मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य अंदर, रचे है विद्या के भव्य मंदिर, ये सर्व सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि, बसी है गंगा के रम्य तट पर, ये सर्व विद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य सुन, रचे है विद्या के भव्य मंदिर, ये सर्व सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि, बसी है गंगा के रम्य तट पर, ये सर्व विद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य सुंदर, रचे है विद्या के भव्य मंदिर, ये सर्व सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि, बसी है गंगा के रम्य तट पर, ये सर्व वेद्या राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर है विश्वकर्मा का कार्य सुंदर रचे है विद्या के भव्य मंदिर ये सर्व सृष्टि
Good morning, sir.
राजधानी।
Morning.
So, sir, shall we start our today's session?
Yeah, we can start, but is it means 11 o'clock already? Because
No,
people will be joining, no? So I think
Don, please wait for some. Please wait for 10 to 15 minutes. People are joining right now also. So let them join. Then after 15 minutes, we will start lecture of Professor Sayandeep Banerjee sir.
okay.
मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी
Sir, one
राजधानी
question I
मधुर
had to ask you.
मनोहर
Hello?
अतीव
Sir,
Yeah.
am I
सुंदर
audible?
Go on.
ये सर्व
Yeah.
Sir,
विद्या की
in between your lecture, if someone wants to ask you any
राजधानी
question, will it be
ये
little disturbing
तीनों
or
Yeah, it would be better if they ask me after the lecture. It would be better. But if someone is having any particular confusion before progressing to the rest of the lecture, then they can stop me. Otherwise, it's better to ask me after the lecture, because I'll be doing some interactive session in the later part of my lecture. Means you guys have to do something along with me. So it's better to directly ask your question after the lecture.
okay, sir, thank you. We'll keep this in mind.
Yeah.
Soham Shri, am I audible to you? Soham?
Yes. Hello.
So, Soham, did you
Yes,
hear
sir.
what sir said?
I have
Yes,
also
yes.
mailed him.
Okay,
Yes, sir. I
then
have
he
checked.
मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी ये
हाँ मदर बोलो। हाँ हाँ मदर बोलो। सर बोले कि बीच में मुझे मतलब रोको मत, मैं बाद में
नए नहीं है ये मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी ये तीनों लोकों से न्यारी काशी सुज्ञान धर्म और सत्य राशि बसी है गंगा के रम्य तट पर ये सर्व वेद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी नए नहीं है ये ईंट पत्थर है विश्वकर्मा का कार्य सुंदर रचे है विद्या के भव्य मंदिर ये सर्व सृष्टि की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व वेद्या मधुर मनोहर अतीव सुंदर ये
Hello.
सर्व वेद्या की राजधानी
Hello.
राजधानी मधुर
Yes, sir.
मनोहर
Yes, sir.
Yeah, I think it's 11 o'clock, so we can start.
Yes, sir. Before start of the lecture, I just want to say something to the participants. Any participant who have any doubt, they can ask their doubt after the session, or whenever sir will allow, they can unmute themselves and ask their query. They can also raise their hand, and the participants who are watching the lecture in YouTube live, they can also write their message or their question in the chat box there. We will pick everyone's question one by one. So you can ask your query. Everyone questions will be discussed. And now Don.
Yes.
Don.
Yes. Hello. Hey.
Now Don, you can start the lecture. Or
So with all your permission, sir, shall I start?
Yeah, please go ahead.
Good morning to all. I am Don Chatterjee and welcome you all today to the second day of our event, URVI, an interactive and exciting geologic milieu. Today we have with us Dr. Sayandeep Banerjee. Sir is a very dedicated and one of the best teachers of structural geology in the department. He is not only a good teacher but also a brilliant scholar. He holds several achievements to his credit, including gold medal for standing first in MSc Geology conducted by Calcutta University. Sir has authored several research publications in reputed high index science journals. Sir, we are fortunate enough to have you today with us. Sir, kindly start this session. It's all up to you, sir.
Okay, thank you, Don. Now, definitely I'll be sharing my slideshow. I think you guys can see it.
Yes, sir.
Okay. So obviously,
Yes, sir.
at the outset, I would like to thank the members of AAPG BHU student chapter for thinking of me as a resource person. I don't know why they have thought of me, but definitely I would like to thank them. And secondly, I would like to thank our head of the department, Dr. BP Singh, Professor Jokhan Ram. Professor Jokhan Ram has been instrumental in bringing actually the AAPG student chapter to BHU. And I would also like to thank Dr. Outcrop Viswas and Professor PK Singh. He was in the inaugural session yesterday. But before I start, I would also like to actually acknowledge and thank Dr. Ashwani Raju means he was actually giving you some details of the basics of remote sensing yesterday, and it is the first of the series of his lecture, and I think it is extremely beneficial to students, be it in means pursuing their graduation or pursuing their postgraduate. Remote sensing is a very advanced and applied kind of tool that you should use during both for your studies and for your research purpose in future as well. And so means I would request all the participants to continue with the series of lecture that is given by Dr. Ashwani Raju during this whole session of URVI. But particularly my lecture is specifically a very focused one. Actually, it deals with a global aspect of tectonics that we generally deal in global tectonics to understand different processes. And obviously, the title of my lecture is Triple Junctions from Plate Scale to Outcrop Scale. And I have chosen this topic actually because of three reasons. First of all, definitely it's a part of our MSc Geology syllabus, and secondly, it will definitely help you to understand other global processes that are going on, means you can say in plate scale. And thirdly, obviously it's kind of exciting, so that's why these are the mainly three reasons that I have chosen this topic. And obviously to start with, here are my lecture goals that we'll be going through. Obviously we'll first try to understand triple junctions, that what are triple junctions. Then we will definitely look into some global examples of triple junctions, and later on we will also do some kinematic evolution regarding the stability of triple junctions, and we will also try to find out the azimuths and magnitude of the relative velocity between plates. We will see this later on. Means nothing to worry about. It includes some basic mathematical calculations that are usually of 10th level or below 10th level. Okay, so starting with the first part, I think. Okay, yeah. So triple junctions obviously are nothing but these are intersecting pairs or sets of simultaneously active plate margins, or sometimes fault, or sometimes shear zones. So when we are talking about plate margins, then we are actually referring to plate scale or global tectonic scale. When you are referring to faults or shear zone, definitely you are referring to regional scale or local scale or based on some outcrops. Obviously triple junctions are common on all scales and in all tectonic settings. Definitely it could be present in some local scale, for example 1:5,000 scale, or it could be present in plate scale, for example 1:10,000 kilometer scale. Okay, and in all tectonic settings, means it could be present in a compressive state setting, it could be present in a transform setting. We'll discuss about transform setting or compressive setting later on. And obviously a wide variety of possible configurations are present, and some examples we'll also deal with, but the mechanics are not fully understood till now, because many research are still going on, but the exact mechanisms are not fully known. So the main obviously objective of our lecture is to understand the triple junction systems. Generally triple junctions, when we say triple junction, it would be anything, like for example there is a plane like this, and not necessary that it has to be a plate 1, plate 2 or plate 3. It could be for example a lithology. For example this is lithology 1, for example this is lithology 2, for example this is lithology 3. So that is also a triple junction. And for example when we do geological maps, to interpret geological maps, many times we actually use these triple junctions as indicators of discontinuities. That for example there is an angular unconformity like this somewhere, and you have some underlying beds like this, and you have some overlying beds like this. So for those scenario also you will get some triple point junctions like this one, this one, this one, a junction between for example bed A, B and X. Then for example a junction between B, C and X. Again a junction between, for example, C, D and X. So triple junctions are obviously means very beneficial to recognize, for example, discontinuities, for example, fault, for example, some kind of angular unconformity or some kind of unconformity. So, but what I'll do here in this lecture, I'll not go into the map scale thing, or we are not here to interpret maps. It's all definitely part of your BSc or MSc syllabus. But what we'll do, we'll actually look into some real examples of triple junctions, be it a triple plate junction, be it means you can say a junction between two faults. So though again, going back to the topic of my lecture, though I have mentioned that I will go from plate to outcrop scale, but for this lecture I will go actually in the reverse way. First we will look into the outcrop scale, then we will come back to the plate scale, because the plate scale dynamics are a little bit hard to means conceive, so we'll deal with that later on. Okay, so looking into the first photograph, that is an outcrop scale example of a triple point junction. Between this, there is a sinistral fault, this is a dextral fault, and those are merging here and they are continuing like this. Okay, so this one is giving a dextral sense of shear and this one is giving a sinistral sense of shear. But if you look very carefully, some are meeting, some are not. So obviously faults or shear zones can meet to form a single shear zone, and this kind of shear zones we generally refer to as zipper shear zone. Why zipper shear zone? Because it looks like a chain. For example, you are opening the chain in this way. Okay, so there is a chain like system, and if you just think of a chain of your bag or your pouch, something like that, then you can see that if you will try to close the chain, then the shear pattern on one side of the chain will be in sinistral manner, and on one side of the chain it will be in dextral manner. Okay, so actually this morphology means, because of this morphology, it is actually referred to as your zipper shear zone. It looks like zips. Okay, so looking at the same morphology or anatomy at outcrop scale, this is an outcrop scale structure. Okay, directly on taken directly on field, and just looking at the tectonic setup of this area, Turkey, Black Sea and Mediterranean Sea, if we look it very carefully, then you can also see that there is Anatolian fault going like this. This is dextral in nature, just like this one. You can say this is dextral like this, this is also dextral, and this one is sinistral like this, this is also sinistral like this. This is the East Anatolian fault. So Turkey is actually bounded by these two faults like this, and there is also a fault going like this. This is the Vato fault. So this is again actually showing you a zipper kind of mergence of your fault zones or your shear zones. So definitely when we are looking into the outcrop scale, definitely they are also present in plate scale, because whatever structure we are looking into small scale are actually also present in the large scale. So your small structures can also tell you big stories about the large scale structures. So if I just try to explain this one here, this is the North Anatolian fault going like this, and this is the East Anatolian fault. This is actually Turkey, this part is actually Turkey. So the main continental part of Turkey is not moving much, but this part is going into a zipper like shear zone, and finally there are some movements along the Vato fault. And a couple of years ago also there has been a small earthquake in the eastern part of Turkey, and people say that this is mainly related to the movement of the Vato fault. So whatever you are looking actually at the outcrop scale, you will also get at the plate scale. You have to have the eye to see it, that whether the processes are local or the process are global. Okay, so Coming to my next example, that is a regional scale example. I'll also deal with San Andreas fault in very detail in the later part of my lecture. But here, if I look into this structure, then you can see that there is a dextral fault like this. Here you just treat it as a dextral fault, not as specific as the San Andreas. We'll later on also discuss about the dynamics of San Andreas fault. Okay, so there is another fault. This is the Garlock fault. This is a sinistral fault, and again it is the continuation of the San Andreas fault. This is actually again the dextral fault that is being continued up to the southern part of the North American plate. This is actually your North American plate. This is the Sierra Nevada region where you have the Sierra Great Valley block, and this part is actually, again in this case, this part, the Mojave block, is not moving at all. But what is going on, due to the zippering of this sinistral fault and this dextral fault, this triple junction that is getting generated by the emergence of these two faults, this dextral San Andreas fault and sinistral Garlock fault, actually due to the zippering of these two faults, this triple point junction is actually moving from this place to this place. Okay, and this is the line where the triple junction was present earlier at 11 million years ago, and this is the present, this black bold line is the present location of the San Andreas fault. So obviously triple point junctions are not static, they are dynamic. They can move from one place to another depending on the arrangement of the fault. For example, this is the mechanism. If you want to see, this part is these figures are actually reflecting the mechanism. So this is the Garlock fault, this is the sinistral one, this is the San Andreas fault. Obviously this is also San Andreas fault. So this part is getting first, I can say, attached over here. Then due to the movement of this fault, this block is moving. But if you look at this part, this is the Mojave block, you can say this part is not showing any distinct movement. Look at here, this part is almost static. So by looking at this mechanism, you can say that when two faults or two shear zone meet at a triple junction like this, the dynamics of the triple point junction changes from here, for example, to here. Okay, coming into other outcrop scale features or example, here also you can see that there are sets of shear zones, or you can also simply say fault. For example, this one is a dextral fault. Again, if I consider this one like this, again like this, again like this, then this part is mainly dominated by sinistral faults. Okay, and this part is dominated by dextral faults. So here I want to just highlight that if you are only looking at this part, if you are looking at this part, then only you will be able to see the sinistral features, that how, for example, this pegmatite veins are getting displaced sinistrally like this, again getting displaced like this sinistrally. Here also it is getting displaced sinistrally. So but the thing is, you have to keep in mind, you cannot constantly, you have to look the whole shear zone in a holistic manner. The thing is that you will end up with wrong interpretation. So if you are only looking at this part, then you may end up with an interpretation like that, okay, it's a sinistral shear zone. But when you are looking at the whole part as well as the meeting or the merging points of the sinistral and dextral shear zone, then only you will be able to decipher, no, this is a zipper kind of shear zone with both dextral and sinistral sense of movements. Okay, so this is the schematic diagram. There are various type. So it is possible that two sinistral shear zone may zip and finally form a sinistral zipper shear zone. That is possible. For example, this one. Here you can say this is from the shear fabric, you can say this is a sinistral shear zone. Again, this one is a dextral shear zone, and finally the outcome is a dextral shear zone. So a sinistral one, a dextral one are combining it to form a dextral shear zone. So many of these features are actually recognizable in outcrop, but the exact mechanisms are not always known. So yeah, this is another example of a field photograph. So this is the main shear zone you are looking into, and these are some drag kind of feature, just like the schematic diagram here, and here also you are getting some drag kind of features like this. So here also I can put some shear sense. So this is dextral, and if I put it here, so this one is actually sinistral. So you can see that dextral and sinistral shear zone are coming from here and actually merging along this shear zone. Okay, so this is also a triple point junction somewhere here, and they will finally merge to form some triple point junctions, for example like this, or for example like this. So there are many categories. I will not go into the detail of this one because this is not the focus of my lecture, but if anyone wants, they can read this paper by Pasher and Platt, published in Journal of Structural Geology in 2016. Okay, now looking into some micro scale zippering from shear zone. Here also, if I look at the micro scale, this is a thin section photograph. Obviously, this is the scale you can see of only 200 micron. There also you can see that there is a rhombus or rhombic fish kind of structure, or mineral fish kind of structure that is present, which is giving you a dextral kind of shear zone, and there are some more fish or rhombic kind of structure that are actually giving you some sinistral kind of sense. So obviously these two features may also meet somewhere to form a triple junction, and they will continue as a zipper shear zone. So whatever, if we look at this part, so whatever we are looking into outcrop scale like this can be also present in regional scale or large scale. Okay, so this zippering process or the formation of triple point junction through zippering process is an important phenomenon, and I'll say not many works have been done on this aspect, but people are now interested on this part as well. Okay, so coming into the plate scale phenomenon, or where we will be looking into triple junctions in plate scale, then obviously to understand that, first we have to understand the types of plate boundaries. So definitely many of us also know that there are broadly three kinds of plate boundaries. One is obviously the divergent plate boundaries, where you will get the reef ridge systems, the mid oceanic ridges. You will get some convergence boundary, where you will get either means, for example, a subduction zone, or if it is a continental scenario, then you will directly get a collisional zone. And there is another one, that is the strike slip, or sometimes it is also referred to as transform fault boundaries or transform plate margins in plate scale. So obviously if I look into this triangular diagram, then obviously one end member is your convergent boundary, one your means end member is your divergent boundary, and the other end member is your strike slip boundary. And in between them there are also some scenarios where we refer to them as transpression, when it is a compression of your strike slip and convergence phenomenon. When it's a combination of your divergence and strike slip, then you can say it's a transtension kind of scenario. Okay, so looking at the plate scale margins, there are many plate margins that are present across the globe. For example, these are your mid-oceanic ridges. This is one of the most large and long mid-oceanic ridges that is present between the South American, North American, and here between the Eurasian and African plate. Okay, so this is the mid-Atlantic ridge system. Here you have, for example, subduction zones like this. These are trenches like this. Okay, so globally, if I now look, that these are the ridge axes that are present. There are mid-oceanic ridges, there are subduction zones like this, with these pin-like things or dented margins like this. So these dented directions are always given to show you actually the means overriding plate. We'll talk about that later on. Okay, so these dented margins are all subduction zones, and these parts, this large one for example, these are all mid-oceanic ridges, and these mid-oceanic ridges are frequently dissected by transform faults, or you can say also strike slip faults like this. So this is a mid-oceanic ridge going like this for example, and in between that you have transform faults or strike slip faults like that. Okay. Okay, so just to refresh us about the relative and absolute plate motion, there should be a different lecture as a whole for relative versus absolute plate motion, but I just like to show you this simple animation that actually shows that Earth is actually moving in a spherical way. But when you are referring to a particular triple junction, means the meeting of three plates at a point, then we will talk about the movement of earth relatively and also the movement on a flat earth. We'll again look at this video once again. There you can see that continuously the movement of the plates in a spherical projection is actually changing.
Sir, voice is not audible.
Hello, hello,
Sir, voice is not
hello,
audible. Yes.
hello.
Sir, your voice is
Yeah,
not
yeah.
audible. Now it is audible. Yes, sir.
Okay, 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 okay. Let me go back from where I started. Can you see the PowerPoint? Yeah, I think.
Yes,
Yes.
sir. Yes, sir.
Okay, 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 okay. So now that we are looking into, I was actually talking about this animation. Yeah. So that the plates are moving in a spherical manner actually, because obviously it's a spherical projection of the plates that you are seeing like this on a spherical earth. And here I was referring to that here the triple point junction you can see also is moving. So it is very essential to note the means you can say the dynamics of a triple point junction, that where at the triple point junction is moving or not. I mean whether it is going in the eastern direction or western direction, to actually assess the movement of the plates that are associated with that particular triple point junction. So looking into the relative rates of the movements of plates, that you can see that somewhere it is quite slow. For example, yeah, for example this is the Great African Rift, where you can see that the movement is only 10 millimeter per year. Okay, so this is the main African plate, and this is the minor Somalia plate. Okay, so here the mid-oceanic ridge, actually a rift ridge system is getting formed, but the movement it is very slow. But if you are looking at a ridge system, for example here between the Pacific plate and the Nazca plate here, somewhere here, then you can see the movement is very high. So obviously the relative motions of the plates are not exactly same everywhere. So they may vary, for example only 10 millimeter per year to up to 156 millimeter per year. It's quite large. Okay, so but as I was saying that we will mainly deal with the movement of the plates mainly on a flat earth, because when we are looking into for example a triple point junction like this, if this is plate A, for example the large plate somewhere, this is also a large plate, and here your C plate is going, so you are actually standing at the triple point junction between, or the triple plate junction now onwards, I'll say not triple point, I'll say triple plate junction from here. And so you have a connection between these three plates here at the triple plate junction. But when you are looking at the dynamics of the triple point junction, generally we consider for example in a regional scale, that where at the movement of the triple point junction is restricted here, or the triple plate junction is moving somewhere, or whether the plates are moving or changing its dynamics with respect to the triple plate junction. So to understand that, first we have to understand that, for example, relative motions we always say with respect to one fixed plate and one moving plate. So means in this case, for example, this first one, we are referring to a plate that is B, that is fixed in space, okay, and A plate, it is moving, and this is a train system or a subduction system. So this is, for example, the overriding plate, and this is, for example, the subducting plate. So this plate is going down between beneath this plate B, and with respect to plate B, it having a motion like this. Again, I mean, if I conceive this the other way, this is again the subducting plate and the overriding plate, but now we are just conceiving that plate A is fixed and plate B is moving in this direction like this, okay. So means whenever we are considering relative motion, then obviously this equation should be satisfied, that the movement of plate B with respect to A is equal to the negative movement of the plate A with respect to B, because it is opposite direction. Because when we are hello, what is going on? Hello, what's going on? Hello,
Yes, sir, I am muted.
hello,
I am.
okay. Okay, so the thing is that we are referring to actually the relative plate motions like this. Okay, so the common types of triple plate junctions, you can say there are plate junctions like this, when this is a ridge, this is again a ridge, again this is a ridge. So these are the plate margins that are actually meeting at this triple plate junction. Similarly, there are some other plate junctions like ridge, fault and fault, or okay, so these are actually referring to, when I am saying R, that means I am referring to a mid-oceanic ridge or a ridge system, okay. When I am referring to F, I am referring to a transform fault system, and when I am referring to T, that means I am referring to a subduction zone or a trend system, okay. So there are many kinds of triple plate junctions like this. So first of all, this one, for example, is a triple plate junction between three ridges. This is one arm of the ridge, this is another arm of the ridge, this is another arm of the ridge. Similarly, this one again is a triple plate junction between a ridge, a fault here, for example F1, and another transform fault F2 somewhere here. Again this one is another triple plate junction somewhere here. So for example, this one is the trench. So definitely the contact between, or the margin between plate A and B will be a trench. Again the margin between plate C and B will be a trench, but the margin between the A and C plate will be a ridge. So that's why triple plate junction, we will call it a ridge transform. Sorry, ridge trench means this is a subduction zone. This is the overriding plate. These both are actually subducting between this beneath this overriding plate, and between these two subducting plates also there is a mid-oceanic ridge like this. Okay. And to keep in mind some basic things, that ridge means in cases of ridge, the relative velocity must be divergent and usually perpendicular. Means that if this is a ridge system, then the relative velocity will be more or less perpendicular to this, okay. So this is the first assumption that are required for quantitative analysis. Okay, now looking at the transform fault, this one, For this one, relative velocity must be parallel to the fault. So always the movement is actually parallel to the fault itself. And for trench, the relative velocity must be convergent, means the relative velocity of plate C and plate A, for example, here are actually converging towards plate B, but it not necessarily that it is perpendicular to plate B. It could be like this, it could be like this, it could form a transpiration kind of scenario that we were discussing in the preliminary slides, that the convergence, if it is oblique in nature, then you can also divide it into two components. One will be strike parallel with the subduction zone, another will be strike normal with the subduction zone. So that will give you a transpiration kind of scenario, means oblique subduction. So in case of subductions, it's not always, the movement is not always actually perpendicular to the subduction zone, but in case of ridge system it is always perpendicular to the ridge system, and in case of transform faults or strike slip fault it is always parallel to the faults. Okay, and okay, now looking at some global examples, like for example the San Andreas fault I was referring to. This is the position of the San Andreas fault when you are referring to the global tectonic framework here, and this, there are actually two triple junction. We'll means again go deep into the San Andreas fault in detail in the later part of this lecture, and there are actually two triple point junctions here. We'll look into the dynamics of this triple point in very detail. Okay, so this is one triple point junction. This is sorry, I'll again refer to triple plate junction. This is, for example, another one where, yeah, looking at the tectonic framework, a triple plate junction present here in the southern part of means Indian plate. Here this is the Carlsberg ridge that is coming right like this. This is the Carlsberg ridge. Okay, this is the actual the ridge between the African plate and the Antarctic plate, and this is another ridge that is coming like this. Between this is the Indian part, this is the African part, this is the Antarctic part. Okay, so these three ridges are coming here at this triple plate junction. Okay, we'll again see some other example like this one. This is actually the Beauvais triple junction. So this is an interesting one also. Okay, for this one I'll name this, yeah, I'll name this one,
me as well.
this triple point junction that is present between the Carlsberg ridge and the ridge between the means your African and Antarctic plate, and also another ridge system present between in the Indian plate and the Antarctic plate. So this one I'll refer to as a ridge system. So this ridge, this is again a ridge, this is also a mid oceanic ridge. So this you can say a ridge system. Coming into this one, yeah, this one, this is the mid Atlantic ridge that is coming like this and ending up just here, and this is again the boundary between the your African plate and the Antarctic plate, like this one it is coming. Yeah, this is another ridge coming like this, and this is another ridge coming like this, that is between the South American plate. This is actually the South American plate, and this is the Antarctic plate, and this part is actually the African plate. If you look very carefully, there is a ridge. This is the southern part of the mid Atlantic ridge. This whole is the mid Atlantic ridge, and this is, we are referring to the southern part. So this is coming here. So this is again a ridge system, this is again a ridge system, but here the ridge is actually ending up into a fault zone or a transform fault like this. Similarly, the southwest Indian ridge is also actually ending up into a fault system like this. So it's a, definitely it's a triple plate junction, but the thing is that the, in this case, though there is a ridge here there is a ridge here, there is a ridge here. This ridge has been dissected by this fault. Again, this ridge is actually by this fault, and this is the continuation of the mid Atlantic ridge, and they are meeting at this point. This is again a triple plate junction. There you can refer it as a ridge fault because definitely this is a ridge, so this is R for that. So this ridge is getting dissected by a transform fault. So that first fault for F, this one, and again the second F for this fault where it has dissected this South American Antarctic ridge and forming the Bouvet triple plate junction. So there are different kinds of or different arrangements of triple plate junction. Here also again there is another example. This is the Eurasian plate. Obviously this is the Pacific plate, this is the Eurasian plate, this is the Philippine plate, and all this margin between here and here like this, these are all nothing but these are subduction zones, and this is the part of actually the, you can say, the Pacific ring of fire that is present here just along the margin of the Pacific plate. So here you will get a subduction zone where the Pacific plate is getting subducted between the Eurasian beneath the your Eurasian plate. Here this is also a subduction zone where your Philippine plate is getting subducted beneath the Eurasian plate, and here is another subduction zone where your Pacific plate is getting subducted beneath the Philippine plate. So here you have a subduction zone, here again you have a subduction zone, here you have a subduction zone. So there are three trenches that are now meeting at a single point. So that is again a scenario of a trench and trench triple plate junction. Okay, so why the analysis of triple plate junctions, or why it is necessary to judge that whether this triple plate junction is stable or not? Definitely it will actually give you an insight about the future processes, that what will happen to the dynamics of a plate margin. For example, if I look at this point where your actually Farallon plate, this is the Farallon plate, this is the Pacific plate, and this is the North American plate. So there is a triple plate junction where the margin is defined by between the Pacific and the North American plate. This is the San Andreas fault, this is the Mendocino transform fault, and this is a simple subduction zone. So also you can say that for subduction zone you will put a T, for example. Here for this transform fault you will plot a F here. For this transform fault again you will plot a F here. So this is a scenario of a TFF kind of triple plate junction. Okay, so why the analysis of this triple plate junction is necessary? For example, if the triple plate junction is moving northernly, for example this is north, and this triple plate junction is moving northernly, then what will happen to a or some structure, for example, that is sitting at this point E? Definitely the scenario will change, because this structure is first when it is not moving, or means for example at T1 time when the triple plate junction is somewhere here. So a structure or person that is standing right here is in a subduction environment or in a compressive setting where the Farallon plate is getting subducted beneath the North American plate. But if the triple plate junction moves, for example northernly here, then the same structure or person who is standing at point E will now be directly affected with a transform kind of scenario or a strike slip fault kind of scenario, because now the triple point junction is somewhere like this, plate junction is somewhere here. Let me draw it once again like this. So if the triple plate junction that was here, so now you will experience a convergent environment here, because here only the Farallon plate is getting subducted beneath the North American plate. But if the triple plate junction moves like this, for example here, now your scenario is something like this. You have the triple plate junction here, you have the Mendocino transform fault here, same subduction is going just above the triple point. But now look at this position. So what will happen to this position? This position will now go into a transform or strike slip kind of environment. So obviously you need to judge that what will be the fate of triple plate junction, what will happen to a triple plate junction, and obviously that whether that triple point junction will be stable or that triple plate junction will be unstable. So to do that, actually there is a quantitative method. We do the analysis like this, that for example we'll start with some basic. For first example is, for example, a subduction zone. From here onward, I would request all the participants as well as my students to definitely have a plain paper and a pencil, and in the later part also a scientific calculator if possible, because we will be doing some calculations and analysis. So here we are, first example, this is a plate A, this is again a plate B here, and the margin between, this is not a triple junction, this is a simple margin between plate A and plate B. So this margin is actually a subduction zone, where for example the B plate is the overriding plate and the plate A is the subducting plate. That means the plate A is getting subducted or going down beneath the plate B. So here in this scenario, if I want to quantify it, then obviously I need a reference frame. So the best reference frame is your geographic direction. So I have taken this north, south and east west direction. So here first I have put, for example, B somewhere here, that B is restricted somewhere here. So with respect to B, what I am seeing, that A is moving in which direction? With respect to B, A is moving in this direction, and again with respect to A, because we are talking about actually relative velocities, so with respect to A, B is moving in this direction. So if I put B over here and A over here, so definitely it is satisfying the scenario that is going on here, because this is the velocity space diagram. We'll call it a velocity space diagram, this one. So if I am putting B over here and A over here, then you can see the relative movement that we are talking about, that B is moving away from A in this direction towards your southwest direction, if this is your north south, and A is moving towards northeast direction relative to B. So this velocity space diagram is actually satisfying this scenario. And again, where your margin will be, because we have considered this B as the overriding plate, and this dented sign is actually referring to the overriding plate, and A is your subducting plate. So your plate margin will be attached to the B like this. So this is your plate margin, or the trace of the plate margin, that is generally referred to as small small alphabets between the plates. For example, it is between A and B, so it will be referred to as a margin between A and B. But as the overriding B is the fixed plate or the overriding plate, this trench will be always attached with the B position, and again the relative velocity between B and A will be like this, where B is moving towards the southwest direction like this, and A with respect to B is moving towards the northeast direction. Okay, coming to the second example, for example, there you have a transform fault. Again you have a scenario of a plate A and plate B. Again this is not a triple junction, we will come to that afterwards, but this is a plate margin between plate A and plate B, where there is a transform kind of scenario, dextral movement is going on between plate A and plate B. Again, if this is not, then plate A is moving towards, mainly towards the northeastern direction, and if this is again north, plate B is actually moving towards southwest direction. So again we'll plot that the positions of A and B in the velocity space diagram, where if I put B somewhere here and A somewhere here, then you can see that the same thing is getting satisfied. The velocity space is actually satisfying this scenario. Why? Because here the A point is moving in the northeastern direction, like that we have already seen, relative to B. And again, if I assume that A is fixed and B is moving towards the southwest direction with respect to the plate A, so this one is again satisfying the scenario of this transform for, or the movement or the velocity space diagram is actually it is satisfying the movement that is going on at this plate margin. Okay, so again this margin is referring to this margin, this small AB margin is actually referring to your plate margin between A and B. So obviously it will follow what, because it's a transform fault, so the margin will follow the movement direction. So that's why the margin that has been given as a dashed line here is actually following the trend of the velocity or the movement direction of plate A and B, like this. Okay, so for example, this one is for here subduction zone, the second one is for transform margin, the third one is for a reach system. The third example, if it is a reach system, yeah, the third one is a reach system where you have a plate over here, plate A, and again a plate B over here, and here in between you have the reach system like this. But here now this is interesting that the movement of the plates are away from each other like this, like this. Okay, because this is a, for example, a mid oceanic ridge between plate A and B. So like I directly discussed earlier, that the movement vectors in case of ridge system are generally perpendicular with respect to the ridge. So if this is the ridge like this dashed line, this is representing your ridge, and always you have to follow this geographic orientation. If this is not, this is more or less going northwest southeast, so you are following this thing. This is also going northwest southeast, and now you have two velocity vectors, one going like this, another one going like this. So directly again from this velocity vector space also you can say that the A plate is moving away from B, as well as the B plate is moving away from plate A. But the thing is that mostly in case of mid oceanic ridges they are symmetrical. Means if, for example, if it is moving at x centimeter per year in this direction, then this part will be also x centimeter per year in this direction. So it is generally symmetrical. So these are the three different kinds of plate margins that can be directly quantified just using a velocity space diagram. Okay, so coming into now a triple plate junction, where you have a triple plate junction between plate A, plate B, and plate C. So the junction, the margin, first I look at the margins. The margins between A and B, it's a ridge. Okay, again the margin between plate A and C, it's again a ridge, like here. So I can write R here, also R, and for this one the B and C, it is a fault. So this is a transform fault. So I'll refer to this triple plate junction as a RRF kind of scenario. Okay, and now if I want to reflect it in the velocity space diagram, then with respect to A, let us first fix one of the plate, for example A, at the center right here. So with respect to A and C and B, so I'll put C somewhere here, for example, and B somewhere here. Why? Because if I look at these two ridges, that you can see the velocity at C is that of the velocity at this position. So definitely A and C are moving apart from each other, as well as A and B are also moving apart from each other, but the rate of movement of A and C is quite slow with respect to the rate of movement of A and B. So if I put A and B somewhere here, then obviously C will be in between them. And the movement line, always you can see this is the movement line. So this is following, this is north, so this is parallel to east to west, so that way it is present in this line. Again, this movement of the ridge across this ridge is also east west, so again this is also present right here. Like this, the movement direction between A and C, as well as movement direction between A and B. And also there is another one, that is between B and C. Here this is also east west, the movement is also east west, as well as the margin that is defined by the small alphabets B and C, that is also going east west, like this. Okay, but there are two ridges, one is between A and C, symmetrical, exactly symmetrical between, or you can say the perpendicular bisector between these 2 points, that is representing your AC ridge, this one, and again the bisector between A and B, exactly the symmetrical the perpendicular bisector, that is represented by the margin A and B. So this is a velocity space diagram of a triple plate junction. That's how you actually draw your velocity space diagram when you are referring to any triple plate junctions. Okay, so now looking at this one again, so this one is one margin that is represented by one ridge, this is another ridge represented by AB, this one, and this AC is this one, and obviously there is another margin between your plate B and C, that is a transform kind of margin, but there is a margin, so that is B and C. So there, can you see any triple point between this margin and this margin? No, because this is not a triple point, this is the margin between this and this is also not a triple point, because not three margins are not intersecting at a single point. But here, when you are just changing or you are progressing with the phenomenon that is going on right here, the movement of the transform fault is actually controlling the dynamics of the triple point. Now you have the triple point junction. We'll see how that first there was a triple plate junction somewhere here, it looked like it's somewhere here, but in the velocity space diagram it is not very clear that where is your triple plate junction. But from this, when the transform fault is actually modifying or actually moving the triple plate junction, then now you have the triple point junction somewhere, triple plate junction somewhere here. Here you have a margin between C, here you have a margin between A and B. So this point is actually the triple plate junction between your plate A, plate B and plate C. The same kind of ridge is present here, where A and B are going apart from each other at a much higher rate with respect to A and C. But also that same transform fault has now actually has become a transcurrent fault. I will not go into very detail of transcurrent fault, but you just try to understand the scenario here, that the same fault is now giving actually two kinds of movements. Here you have a dextral movement in this part between B and C, between A and C, this is all A, this part is also A, this is also A. So between A and C you are actually getting a sinistral kind of movement. Okay, so this is actually the same dextral fault that was present here due to the varied rate of movement of the ridges between A and B and between A and C. Because the rate is higher here, the rate is comparatively slower here. So here, due to the varying rate of the movement of the ridges, here it will go in a faster rate, here it will go in a much slower rate. So that's why, due to the relative movements of these plates, plate A on the left side of this margin and plate C on the right side of this margin, here you are getting a scenario of a sinistral movement and resulting into a triple plate junction somewhere here between your plate A, plate B and obviously plate C. So now if I want to analyze the stability of this triple plate junction, then always I have to again draw a velocity space diagram. Again this is for example north, and these are the margins. This is between, for example, A and B. Okay, first we'll fix plate A. We'll go the normal way. This is A. With respect to A, B is moving apart from A at a much higher rate, like just like the last example is the same thing. And you also have C sitting right here with a much lower rate with respect to your movement of A or B. So that's why it is in the middle. So now looking at the margins, here you have two ridge, one ridge, again a ridge here, and this is a transform fault. Okay, so that one would be a ridge fault kind of triple plate junction. But for this one, you can see that now the triple plate junction has moved from this ridge up to here. So now between A and C also you have a transform fault kind of scenario. Only between A and B it is mid oceanic ridge. Otherwise A and C is a transform fault. Also B and C is a transform fault. So if I draw the margin like this, and transform fault will always follow the velocity vector. So obviously this is one margin, one F, another F, the one F representing the margin between A and C, that is one fault, one transform fault. Again another one, another transform fault representing the margin between B and C, that is F2 for example. So they will lie just along east direction like this. And now you can refer to a triple point junction where your two margins, your F1 plus your F2 plus your ridge, this ridge between A and B, plate A and plate B. Now these three are actually giving you a triple plate junction, and this triple plate junction is where it is actually sitting at the intersection of all the three margins. Means like this, if I consider again a triple plate junction, then the triple plate junction should be present at the intersection point of all the three arms, or all the three, be it a ridge, be it a fault, be it a trench, whatever it is. So it should lie exactly at the intersection of all the arms of the plate margins like this. Okay, so okay, now let's go to another example. That is a scenario where you are having a triple plate junction sitting somewhere here, and you have a transform fault like this. In this part you have a subduction system in this part between A and B, and you have a ridge system somewhere here. So if I again want to analyze this in velocity space, then I will take it, or I will draw it one by one. Means I will first take this arm, the subduction arm, again I will take this fault arm or the transform fault arm, and again I will take this mid oceanic ridge arm, and then means finally I will combine all three to get the actual velocity space. So example, for this one, this is the trench, this is plate A, plate B, this is again the overriding plate, because this is the dented margin that is present at the overriding plate. This is the subducting plate. Again, like we have seen earlier, that if this is the margin, B will be attached to the margin, because this subduction zone will be always attached with the overriding plate. So B will be attached to this margin, and also you have to follow this direction. With respect to north, it is northwest southeast. So this is also going northeast southwest like this. And with respect to B, the velocity of A is in the northeastern direction like this one. So again we'll put somewhere A. It actually, the magnitude will be defined by the rate of movement. For example, this is 5 centimeter per year. So you will take 5 unit from your graph paper when we'll do it in some graph paper. But right now we are doing it on a simple plain paper. Okay, so looking at the second arm, that is the fault arm or the transform fault arm here. Here you are also getting a dextral kind of scenario or dextral a sense of movement. So looking at the velocity space diagram, again we'll put the margin first. This is the margin. This is again trending with respect to north. It is trending northwest southeast. So it is like this. We'll put small b and c because it represents the margin between plate b and c, and obviously the movement between b and c, the b is going towards southeast and c is going towards northwest. So again if I restrict c somewhere here, then depending on the relative movement we will put again b somewhere here, and depending on the magnitude of the vector, that whether it is 3 centimeter per year or 5 centimeter or 10 centimeter per year. Similarly for this one, this third arm now, the ridge one, again we'll draw the velocity space diagram like this. So again with respect to north, you have to always consider this reference frame. For example, north or south east west, this reference frame you always need. Again the ridge system is now here is trending more or less towards the northeast and southwest direction. So again we will draw it like this with dashed line. This is the margin between a and c like this, and obviously if you remember that it will, this margin will actually bisect, let me take another one. Yeah, the margin will actually bisect the velocity vectors like this. So this is actually perpendicularly bisecting this vector. So if this is c, for example, again fixed with respect to a, they will move apart from each other again in a symmetrical way. But if we fix c in a velocity space like this, then we'll take that whole magnitude or the magnitude of the relative velocity and we'll put a somewhere here. Similarly, if I now see the trend of the vector, then it is actually more or less in the northwest southeast direction. So it is also following this. Okay, and the margin is actually bisecting the velocity vector between c and a. So now if I combine all three, obviously it's a fault, means the transform fault, trench and ridge system. This is the transform fault, this is the trench, and this is the ridge system here. Okay, so this is a scenario of FTR scenario, and by combining all three, coming from here, this one, then obviously this one, and again finally this one. Yeah, so if I combine now all three with respect to all the three arms, it will end up to a scenario like this. So this is the velocity vector between, again we can check that the AB and BC margin, AB margin and BC margin, that is trending more or less northwest southeast. So this is the margin. Okay, so this is the first one. The second margin is this one, sorry, the third one, because both are oriented in a similar manner. So this is the third margin between plate A and C. So this is the another margin. With respect to north, it is oriented mostly in the northeast southwest direction. So this is your AC, like this, going like this. Okay, and now you have the velocity space or the velocity vector. So between A, B, C, you can compare and check whether you are correct or not. So from here, with respect to your A and B, with respect to B, B is fixed again because it is the overriding plate, for example, and A is in this direction, so this one is correct. Again with respect to B and C, it's a transform boundary between B and C, so the velocity vector will lie along the margin. So it is lying along the margin between B and C, but B is moving towards the southeast direction and C with respect to B is moving towards northwest. So again it is also correct. And finally between A and C, this is A and C, the margin should be the margin should bisect the velocity curve like this between C and A, so it is also bisecting. And if I look at the trend of the movement of A and C, then A is moving towards and C is moving towards northwest. So from the velocity curve also, velocity vector also, you can say that A is moving towards southeast and C is moving towards northwest. So just by doing this quantitative analysis, you can predict that whether your triple plate junction will be stable or not, because now you can see that all your margins like this are actually meeting at a same point. This is your triple plate junction between plate A and B, between plate B and C, and between the margin of plate A and C. So all they are meeting at a single point. So now you can say that if they are meeting at a single point and they are giving you a triple junction, or sometimes it is also referred to as simple J, then your arrangement of the plates or the fate of the triple junction will be stable just by changing the orientation a little bit. Look, this is the fault scenario, this is subduction scenario, this is ridge scenario. We are just changing a little bit the scenario here. Sorry, we are not changing a scenario, we are changing the arrangement, the morphology of the plate margins like this. So this one is again ridge, this is fault, this is subduction zone. So again this is subduction zone, this is fault, this is ridge. So the pattern is same, but the arrangement is a little bit different. Okay, so now if I again draw the velocity vector for all these margins with respect, now you can see that all these margins are not meeting at a single point. So from this you can say your triple junction is not stable, it's unstable. So when you are looking at a triple junction like this, when all the margins are actually meeting at a single point, that is actually your triple junction, then only your margin is stable. That you have to keep in mind. And when they are not meeting at a single point, there is a intersecting point, there is another intersecting point, there is another intersecting point, but they are not meeting at a single point. So in that case you will refer to that triple junction as unstable, and always the unstable triple junction will try to become stable by changing the arrangements or by movement, or relative movement of the plate margins. So this is an example of a fault, trench and ridge system. Again, for example, this is a trench system, means all these margins are subduction zones. For example, this is between B and C, this is the overriding plate, this is the subducting plate. Between A and B, this is the overriding plate, this is the subducting plate. And again between A and C, this is the your overriding plate, and this is the, now this will become a subducting plate when you are only considering this part. But if you are considering as a whole, then C will act as an overriding plate with respect to the contact or the margin between B and C. For this one A and B, the A is acting as an overriding plate and B is acting as a subducting plate. So this is actually the scenario that is more or less going on in the Japan trends. The example I have just shown you earlier, the trend system that is present between the Eurasian plate, Philippine plate and Pacific plate. So there you have three trenches that are meeting in a single point, that is your triple junction. So for example, this one will also means it's better if you guys can draw this velocity space on your own, means on a plane of paper if you have it. Then I will also prompt you that how to draw it like this. If I continue, then you have, obviously again this is north, I am referring to, this is north, for example this is east. Then let us first consider as A is the overriding plate for both of these margins, be it between A and B and between A and C. So if I can fix A somewhere here like this, okay, and definitely if it is the overriding plate, the trenches will be attached to that point. This A will be attached to this one, okay. So now I can draw the margin between plate A and B through A, and what is the orientation? It is north south. This is AB, this is going north south, so I'll draw it through A, north south, okay. Then for example this is again a trench that is going in mostly I'll say northeast southwest direction between A and C. So this is A and C, and again the margin will be attached to A because A is means your overriding plate with respect to C, so the margin will be attached to A. So this is again AC like this, okay. And finally you have also the margin between B and C. So this is more or less a very low angle with respect to east, for example 100 degree or 110 degree. So this will be something like this. So this is B, okay. And if I also refer to the velocity vectors, then look here, C and B definitely you have to measure the angle between this one and this one and this one, and then you have to put it here with the help of a protractor. So if I look at the velocity vector space, then with respect to A, C is moving towards in which direction? In this direction. So with respect to A, C is moving in this direction, fine. With respect to A again, B is moving in the which direction? This direction, okay. So again I can put it like this, and with respect to B and C, B is moving in this direction with respect to C. If I consider C as the static one momentarily, then B is moving in this direction. So now your velocity vector space is complete, and you can see that just by analyzing the trend of the trenches as well as by putting the velocity vectors in a space in a reference frame like this northeast, for example, you can evaluate that whether your train system in this case is stable or not, because all the margins again are meeting at a single point. So this is your triple plate junction, TJ or simply J. So this is definitely a stable situation here, okay. So again going to the the next one, the same scenario of this one, train system where it is stable. The scenario is again same, but the arrangement is now the velocity vectors are now in a different manner. For example, here it is mostly trending, for example 110 degree, but here it is trending in a, for example, more 140, you can also write the 320 degree. So this is another scenario where your velocity vector is changing its direction. For the same arrangement of trains that we have just seen, that it can be stable in a scenario like this, the same arrangement can become unstable when you are having a scenario like this. So actually the stability of the triple junction is definitely a function of two things. Obviously the trend of the margins, how your margins are arranged with respect to one another, and obviously the movement of the plates with respect to one another. So it depends on both, whether your margins will cut at a single point or not, as well as your velocity vectors or the intersection of the velocity vector will lie on that triple junction or not. Okay, so coming into the next one, another example of a trench fault. So this part is a subduction zone, this is a trench between B and C, this is again a fault between A and B, and again between A and C another fault. Okay, so now if I, this is very simple one, because the trend of B and C and A and C is going north south. So this is the trend, this is going north south, B, C, AC again, and between the plate A and B the margin is trending east west. So this is the margin trending east west, AB. So now you can also see that all the margins are actually intersecting at a single point. So this one also you can refer to as a stable triple plate junction, and it will not be dynamic, it will be static unless you change the arrangement of this plate margins. And again, if I satisfy it with the velocity space, you can also draw actually a triangle like this, like we have done previously. So here also A is moving towards west with respect to B. So A is moving towards west with respect to B. A is moving towards north with respect to C, or C is moving to with respect to A, it is moving towards south. So C is moving towards south with respect to A, and between B and C, this is C and B, they are in a direction, for example northeast southwest, like this. So like this you can draw the velocity space diagram, and you can directly assign that whether your triple plate junction is stable or not. In this case, this is a trains fault scenario. So this arrangement is stable, not necessarily that this arrangement is also stable. For example, if you change, if there is a fault, there is a fault, and your trench is like this, it does not mean that that arrangement is stable. But in this case, this particular arrangement of your margins or your triple junction here is actually stable. Okay, just I was talking about this. Only if I change the margin from here to here like this, if I rotate it anti-clockwise like this, the trench is like this, again the same scenario of two faults like this. Then see that you are no longer having a triple point junction, you are having junctions between AB and BC here, you are having junction between AC and BC here, you are having junction between AB and AC here. So again you are not getting a perfect triple point junction. So in that case the same trains fault scenario will now become unstable. So based on this velocity vector space analysis, you can directly analyze that whether your triple plate junction is stable or not. And coming to this one, the ridge, this is the most stable kind of scenario you will ever get in triple plate. In case of triple plate junction, here you have ridge, here you have ridge, again here you have ridge. There are three ridges, and like that, just I have just shown earlier that this is the velocity vectors between A and C. They are going away from each other symmetrically like this, and this is the margin between A and C. Similarly for B and C, they are going away from each other. This will be the margin that will bisect the velocity vector. For A and B, they are going from each other, and this margin will bisect the velocity vector like this. So all these will definitely cut. In general, all ridge systems are generally stable. So, and or you can directly say this is the most stable form of triple plate junctions. Coming to another example of ridge, trench and fault, here also this thing you can directly rather I'll skip it because I've given so many examples. Okay, let's do it the last one. This is a fault, this is a subduction zone again, this is the ridge. So again you can draw the velocity space like this with respect to C, with respect to B, and with respect to A there should be a line like this also. So this space, and you have margins, because between B and C again the transform fault will follow the velocity vector. So this is the margin between B and C. Again the subduction zone of the trench will be attached to C. So your AC margin will go through C. So this is the trend of your two margins, the fault and the trench, and you have a ridge going like this. So this is your ridge. So again this one is a stable arrangement because all the three margins are single point. If they are not meeting at a single point, then definitely they will be unstable. So there are actually total of 16 scenarios that you can see in any global tectonics book. For example, Moods and Twists or Carrion Wine is given. So means there are multiple scenario where you will judge that whether, for example, I was discussing that if it is RRR, then it is all orientations are stable. Okay, so there are 16, but mostly these 16 around 10 have been recorded across the earth, but are still now hypothetical. No records have been found for the rest 6 margins, but you can see all the arrangements in dynamics of or global tectonics, be it Moods and Twists, be it Carrion Wine. Okay, so now we'll directly move on to the natural best example of a triple, where I'll start with this simple animation where you can see that the Pacific is moving in this direction, and your Farallon plate, actually I'll repeat it once again. Okay, I'll go slowly. Okay, so yeah, okay, let's pause here. So the Pacific plate in here, this is the East Pacific rise, the mid-oceanic ridge that is actually separating the Pacific plate from Farallon plate, from Cocos plate, from Nazca plate, whatever it is. I'll show you the exact position of this thing is somewhere here. Going to the first one, yeah. So I am now referring to this part, the processes that are going on in this part. So this is the Pacific plate, and this is the East Pacific rise. So this is the Pacific plate, and there is another plate that is the Juan de Fuca plate that is very small here, but we'll see how it has become Juan de Fuca plate. Otherwise it was earlier a single plate, that is Farallon plate here. So if I progress with this animation a little bit, okay, now what is happening, that earlier this plate was obviously a part or the symmetrical part of the Pacific plate, I mean, or the eastern part of the East Pacific rise. Then during subduction, what happened? Okay, so during subduction, it is getting subducted beneath the North American plate, and it is getting divided actually into two plates, the two new plates I'll say, because the older plate has been subducted, the Farallon plate has been subducted enough. So now there are two triple plate junctions here, one between the Cocos plate, the Pacific plate. The Cocos plate is somewhere here beneath here. So here you have a new plate, that is Juan de Fuca plate, JDF you can write. So this is the Pacific plate, this is the triple plate junction between Pacific plate, Juan de Fuca plate, and North American plate. So this is again a triple plate junction, we'll see in a schematic diagram, and you have another triple plate junction somewhere here, that is between your Pacific or North American plate. So looking at the schematic diagram, so there is a schematic diagram over a period of 20 million years. So where your Farallon plate has actually subducted between the North American plate like this, and due to this subduction, and the Pacific plate is going like this. Actually, the Farallon plate is going like this, and there is this is the East Pacific rise. This ridge is actually the east. What happened? Yeah, East Pacific rise somewhere here is the same East Pacific rise from where your Pacific plate and Farallon plate are going away from each other. The Farallon plate is getting subducted beneath the North American plate. This is the North American plate, And here, just after subduction of this ridge system, excitingly, this is the only example where momentarily it was a quadruple junction. It was not a triple point. When the ridge was actually touching it, you have a quadruple junction between Farallon plate of this part, Farallon plate of this part, Pacific plate here, and North American plate here. So this was a quadruple junction for some moment. Then it broke up into actually two triple junctions, because quadruple junctions are not stable at all, because you cannot find any means point where your four margins will means intersect at a single point. So that's why quadruple plate junctions are not possible. So here you have a triple point junction, here you have a triple point junction there, but the anatomy of the triple point junction is different. Obviously this is the San Andreas fault that has been generated after the subduction of the Farallon plate. Now this plate is referred to as Juan de Fuca, and this plate is referred to as the Cocos plate. So the anatomy of this triple plate junction is different from this, because here you have a fault scenario, again here you have a subduction scenario here. So it's a, you can say, FFR or RFF, but in case of this triple point junction the scenario is different. You have a fault system, you have a ridge system, you have a subduction system. So in this case, for this triple point junction, I'll refer to as is RTF, means ridge, trench and fault. For this one I'll refer to this one as TFF, means trench, fault and fault. Okay, so these are the two triple junctions that are means at some time they were going away from each other, and again due to the dynamics of the Pacific plate or the subduction of this East Pacific rise, again they are coming towards each other. But now this dynamics has again changed. This ridge has been completely subducted here. Here in the later stage, you can say, in the early stage it was a scenario that there are two triple junctions, one with the configuration of trench fault, where you have a configuration of ridge, trench and fault. But now here in the later part, or now in the present scenario, this is the present scenario, the present condition of the San Andreas fault or this margin. Now you have a trench system here and fault and fault. So you have a TFF scenario of this triple junction, and again you have a trench here and F. So now the configuration of both the triple junctions have become same, but it may further change. This ridge will come after the subduction of this whole fault. This ridge will again start to subduct here. So again it will go back to a scenario like this. So always the configuration of the triple plate junction will determine whether it's a stable or it's not a stable one, and whether it will remain static or it's a dynamic one and it will change. For example, another specific diagram, for this one I was referring to, that this is the triple point or the triple plate junction between the Juan de Fuca, you can say, or the remnant Farallon plate. Also here also you can say Cocos plate or the remnant Farallon plate. So here so at this position somewhere here I am referring to junction when it is actually giving you two triple plate junction of trench, fault and fault. Here you are getting what? Ridge, trench and fault. So these are the two scenario and two velocity space diagram where you are getting triple point junctions here, and again now these are present scenario where you are getting your trench, fault, again you are getting your trench, fault and fault. So now you have a TFF situation for this triple point, also you have a TFF situation for this triple point. So now looking at the velocity space diagram for this one, this is the Pacific plate, this is for the North American plate, this is for the Farallon plate. So obviously the Pacific plate and between Farallon plate there is a transform boundary. The Farallon is moving right hand side or easterly with respect to the Pacific that is going westerly. So you can draw something like this, Farallon here, Pacific here, and again between Pacific and North American again is the San Andreas fault, or it is going something like this, that the Pacific is moving northwesterly and the North American plate is moving southeasterly. So again you can draw something like this, and with respect to now North American plate and the Farallon plate, again you are getting a trench like situation where your North American and the Farallon plate is getting subducted beneath the North American plate like this, like this. So for this you have the velocity space like this. Now about the margins. For transform fault, I have mentioned earlier that the margin will follow the vectors. So it is like this, and also for this fault it is like this, and for the trench also, because this is the overriding plate, this is the subducting plate. So the trench or the T junction or the F and Fn will be attached to the northern plate like this. So this is your velocity space diagram of the current situation of the San Andreas fault. So from the current situation is not comparatively, it's obviously stable because the margins are meeting at a single point here, over here. Okay, so from this one onwards, I would like you all to unmute your mic so that you can analyze this and tell me your answers, whatever you can calculate. Hello. Hello.
Yes, sir, you are audible.
Yeah. So it's better you guys can. Hello. Hello.
All the participants, please. Please.
Okay, from here onwards. Hello. Yeah. Hello.
Sure, sir.
Yeah. From here onwards, I want you guys things along with me. So for example, this is my last lecture goal that I already mentioned, that we will find out that what could be the means azimuth or the relative velocity between plates, as well as what could be the orientation of a ridge of a fault in a triple point triple plate junction. For example, this is the first example or the first problem for all of you, that this is a setting of a ridge system where you have a ridge here that is trending 000 degree. Now you have another ridge here that is going 110 degree, and you have to find out the exact orientation. Definitely the system is ridge, but you have to find out that whether this is trending, for example, 200 degree, or it is trending 220 degree, or it is trending 240 degree. So to do that, what you have to do? So first, obviously, you have to get the velocities that you have already given here. So this is the velocity that is already given here, sorry. Yeah. So this one, with respect to plate B and A, the velocity is actually 100 millimeter per year. So if I write, for example, A over here and B over here, then B is moving away, relative velocity. I am always actually talking about relative velocity. So your B is moving with respect to A at a rate of 100 millimeter per year. Again, with respect to B and C, like this. With respect to your B plate, the C plate is moving at a rate of 80 millimeter per year, and this angle is actually 70 degree. How? Can anyone tell me this? how this angle is 70 degree? Because actually the spreading is perpendicular to this one, this B series, the spreading will be perpendicular to this one. So if this one is 110, then the spreading will be in this trend 020 and 200 here, okay, and you have this one is your 090 and you have 020 here. So that's why if this is 70 degree, this is the vertically opposite angle, this is also 70 degree, but you don't know this angle because I have not mentioned the exact orientation of this ridge, so that you have to find out. So for that there are actually two ways. First, obviously, okay, I'll stick to this one, this diagram. Okay, this one. So so you have a triangle here, but it is not a right angle triangle. But if it is a right angle triangle, in means in that case you can directly apply the Pythagoras theorem. That is, for example, this is C, for example this is A, this is B. So if it is a right angle triangle, then you can directly apply C square is equal to A square plus B square. But if it is not a right angle triangle, then you have to follow the law of cosines, where your C square is equal to your A square plus B square minus your 2ab cos alpha. Okay, so from this, your alpha angle is actually here, it is 70 degree. So from here you can directly calculate the value of C from the root over actually a square. Here your a square will be for example this one 80 square plus, directly you can also write, for example 100 square plus 80 square minus 2 into 100 into 80 into cos 70 degree. Can anyone calculate and give me this answer? Hello, hello.
Just a second, sir.
Yeah, we can apply this actually the equation to find out the relative velocity of the third plate, because means for example if it is a right angle triangle, then it would have been 90 degree, this cos alpha, then this whole thing becomes 0, so that satisfies your actually right angle triangle scenario. But when you
It's
are
0.34.
what,
It is
0.34. Cos 70 equal to
which one is
0.3.
0? No, no, not only cos 70, I am actually, means I need the whole one, means root over this thing, 100 square plus 80 square minus 2 into 100 into 80 into
104.53.
right, right, 10.5 millimeter per year. So from this simple calculation you can find out that the relative velocity of this plate between or the relative velocity between plate A and C is nothing but 104.5 millimeter per year. Okay, so that is the first part, that where you have calculated the relative velocities of the margin between your plate A and C. And but you need another thing. What you need to find out what, this one, the azimuth of the ridge, that in which direction your ridge will be present, that also you need to find out. So for that again we'll apply simple trigonometric calculation again, that is the law of your law of sines, where you will get this equation is for sine alpha by A will be your sine beta by B is equal to sine gamma by C. So by just applying this equation, now I think you will be able to find out this alpha. So from this equation I can write, for example, sine alpha by this opposite arm will be your 80 will be equal to sine 70 degree, this one, by your this arm, that is 104.5. So from this you have to find out the alpha angle. Again, sine alpha by 80 is equal to sine 70 degree by 104.5, that we have already calculated. Yeah, from this someone calculate and give me the value of alpha, then I'll check that whether you are correct. So you can write sine alpha is equal to 80 by 104.5 into sine 70 degree. So, so finally your alpha will be sine inverse of this whole thing.
46.05.
Yeah, 46.00.
Right. So, so if you have alpha is equal to how much? 46 point.
46.0034.
Okay, then
0.05.
okay, then okay. Then we'll consider it as 46 degree. So, but this arm is in this quadrant. This is west. This is
46400.
so. If this is 046 degree, it is coming. Then it is actually referring to your 226 degree, because we already know this ridge is not in this direction, it is in this direction from the velocity space. Okay, so the azimuth of your ridge that is not known earlier, you can calculate from this trigonometric solution, because it has given you an angle of 046 degree. This is in this direction, so I'll take the simply the other strike end of that, because we already know that the ridge should lie somewhere in this quadrant, as the velocity space is like this, so it should be something like this here. Okay, are you satisfied? Hello?
So can you explain again
Yes, sir.
Which one?
the direction one, sir?
Yeah, we have, look what we have got here, that this angle, this alpha angle is actually 46 degree.
Yes,
Okay,
sir.
so it is actually referring to your 046 degree here. Hello, someone started presenting or something. Hello?
Yes, sir.
Yeah.
Hello.
So
Sorry, sir,
this
for the
alpha angle,
disturbance. Dear participants, please, all of you, mute your mics. Then bandwidth will increase and everyone will be able to attend this. Please, everyone, please, do the required. Please mute the mic. Uh,
Sir, now you share your screen.
Sir,
Now you
now you
again
can
share your
continue,
screen.
I guess. Sorry for the interruptions.
1 minute. Yeah, okay. Yeah, so I was referring to this one, that this angle has now, you have got, this is 46 degree.
Yes, sir.
Okay, and so this angle will be how much? If this is 46, if this is 70, then this angle
66.
how much? Hello?
64, 64,
64.
64 degree.
64.
Right,
64 degree.
64 degree.
64.
Yeah. So have an arrangement of this one like this earlier.
That's
Okay.
64
When
degree.
we yeah. Means I have
Hello.
already written it. Yeah, I have already written it. It's 64. Yeah.
Hello, am I
Look at
audible
this one.
to everyone?
Yeah. Yeah, you are. Hello. Hello.
Hello, sir. The screen stopped sharing. So can you please share it again if it's possible?
Sir, the video has been stopped, I guess. Video has stopped.
Now. Now can you see?
Yes, sir. Yes, sir. Thank you.
Yes, sir, it is visible.
Okay. Okay. So I was referring to that if this angle that you have just calculated, this is 46 degree. Okay. And
Yeah.
and definitely this angle will be your 64
60.
degree. Okay.
Yes, sir.
Okay. So now you have already you have the arrangement over here. This one is your 00 degree. Okay. And this one is your 110. Respect to your 110, this one will be perpendicular. The spreading across this ridge between B and C. Okay. So that spreading will be perpendicular. Means this line.
Yes, sir. Yes.
Okay. And so from here I can also draw this one, an angle of 64 degree. Like this I can draw.
Yes, sir. Yes.
I mean, this one is not exactly 64, but something like this. Yeah. Something like this. So this
Yes,
is
sir.
64, and you also know that you have the alpha angle 46 degree with respect to east west. So if you draw this one, alpha angle, so this one also you can draw with respect to east west. You have 46 degree. Okay. This
Yes,
one
sir. Yes, sir.
46, 64, this one 70. Now obviously this spreading rate or the velocity vector of this spreading will be also perpendicular to this ridge. So what you have to draw, you have to only draw a perpendicular to this velocity line like this that I was showing you earlier, that the spreading ridges or the mid-oceanic ridges of the velocity between plates. For here
Yes.
C plate, so once you have this line, so on this you can directly draw the bisector. So from that you can directly measure the azimuth. Right, from 00 degree you can directly measure it.
Yes, sir.
Okay, so from alpha angle you can calculate the orientation of the other ridge that was not known earlier. So I mean by this simple trigonometric calculation you can first of all you can find out the velocity of a particular or the relative velocity to be specific of a particular, and from that also after finding out the velocity of the third plate you can also find out the exact orientation of the ridge, that whether the ridge is like this, whether the ridge is like this, whether it is like this. Okay. So that is one example. Coming to the second one, this one you guys try to do it, that for example both plates A and B are being subducted between beneath plate C. Here means this is the overriding plate for both A and B plate, and B is the overriding plate in case of A. So what will happen? Again plate A is also being subducted beneath plate B along a trench that has an azimuth of 135 degree with respect to the triple junction. We assume that the velocity of plate A relative to plate B has a magnitude of 50 millimeter per year. Directly I have also given the diagram of the velocity space. So now it's your turn to draw the, means find out the magnitude sorry, not the magnitude, the azimuth of the trench between your C and A, and yes, obviously the magnitude. So you have to simply do it in the manner just I have shown you, like this. You have to do it in the same manner, and you guys have to tell me the answer right now. Are you doing it?
Yes, sir.
Yes, sir, they are doing.
Yeah. Okay. So again, if I also try to do it here, this is 135 degree, this is alpha, this is this. Okay, so let's try to do it. So UAC will be again
92.72.
92 point,
72.
right. You can also consider simply 92 or 93 if you want. Okay, and the second part, what will be the alpha angle? That also you have to find out. You can write sine alpha here. You can do it sine alpha by this, and is equal to your sine 135 degree by your 92.4 or 7, whatever you have got.
Is it 22.6?
Alpha, yeah, right. I have calculated earlier at it is at 22.5, but okay, 22.6 is perfectly done. Okay, so obviously from that also, like just I have shown you here by finding out the alpha angle, and you already have the other angles. This is actually 2.5, so let it be, for example, 23 degree. Then it will have uh, some other angle, 23 plus this one means your 158, means this will be your 22 degree, or both actually 22.5, 22.5 degree. So based on this also you can directly, yeah, both will be actually 22.5.
Yes.
So from that also you can find out the trend of the trench between plate B, C and A, like the last one I have shown you. Okay, coming to the last question here, this one also you can do it. That consider this one, I have not given you the diagram, so you have to draw it yourself. That consider an RRR triple junction of plate A, B and C. The ridge between plate A and B lies in a north south direction. It is given almost an azimuth of 0 degree with respect to the triple junction, and has a relative velocity of 60 millimeter per year. The ridge between plates B and C has an azimuth of 120 degree with respect to the triple junction, and the ridge between plates A and C has an azimuth of 270 degree with respect to the triple junction. Determine the azimuths and magnitude of the relative velocities between plates B and C and A. So for this, I'll help you a little bit to draw the diagram. This is more or less the scenario I have given. This is plate A, this is plate B, this is plate C. This is 000 degree azimuth, this is 120 degree, and this is 270 degree. Now it's up to you to draw the both the velocity, space, and azimuth and magnitude of the means direction and magnitude of the relative velocity, in which direction the plates will move, and as well as the magnitude. So it's first better to draw the velocity space diagram I have shown earlier. If I, for example, restrict A here and you have B, because all are ridges, so the spreading will be more or less symmetrical and perpendicular to each other. So this will be B, and obviously this will be C. And this one you already know, this is 60, I guess, right? 60 millimeter per year. Yeah, so this is 60 millimeter per year. This is 90 degree, because this is 0 and this is 270, so obviously this would become 90 degree. And if I also consider this symmetrical spreading, if the trend of the ridge is 120 degree, then the spreading will be in obviously minus 90 and plus 90, means 030 and 210 direction. So this is your 210 direction, this is your 030 direction. And with respect to this, again you have, this is your 60 degree, this will be your 30 degree. I think that would be enough for you guys to assess the relative velocities and direction. Here one more clue, you don't have to use the law of cosines, you can directly use the law of sines, because you have all the angles, you don't have to find the angles here. So for that you can directly apply this thing. For example, sine 30 degree by 60 is equal to sine 60 degree with respect to this, means velocity of CA. From there you will get one, from another you will get another. So let's see your answers.
Sir, sorry to interrupt you. Can you please mention? Can you please mention how the angle B comes 60 degree? I have a doubt from the first question, but I don't ask you that how the angle B is come 60 degree. Or we are considering a perpendicular from 120 to it is 030 and here is 210.
Right. Okay.
So here, so
line,
what line?
But the AB line is 090.
Yeah, AB line is 0 east to west direction 090.
Yes. So this angle 030 and 090 will be how much? 60 degree.
Okay, sir. I got. Okay.
So this one will be also 60 degree. The vertically opposite angle,
sir.
right?
Okay, sir.
Sir, I got the
answer. It's 104.1 and C and out. With C and it's 120.
This is the answer. You guys can check. So this is what you have got.
103.8.
Yeah, 103.7 means it's 104, you can say. Okay, so the direction of the movement of the plates B and C, or with respect to the relative velocity between plate B and C is obviously 120 millimeter per year, but in the direction of 210. And in case of the relative movements of C and A, the movement rate is 104 millimeter per year, but the direction is like this. So the direction of this one will be in 0 degree, the direction of this one will be obviously in 210 degree. It is already given in the question. So yeah, all you have to find out is the relative movements here. Okay, so I think that is a very long lecture, but I have tried to actually given you whatever I could means in this lecture. Okay, but the last question remains, that why a triple junction of three transform fault cannot exist. For this you can look at this diagram. This is FFF, this one is fault, again this one is a fault margin, this is also a fault margin. So whenever you will put it in a velocity space diagram, always the margins will follow the velocity line, so it will never form a triple junction. So it's not possible to have a fault kind of transform means triple plate junction. Or if it for example, if it forms for a momentarily a time also, then also it will get transformed to some other kind of for example, this will become a trench, or this one may be replaced by mid-oceanic ridge, something like that. Otherwise this fault scenario is not stable and it's not possible. So but before I finish, I would like to acknowledge some of the stalwarts of global tectonics. Obviously means these people, whatever I have discussed today actually is the result of the research and hard work of these people for many years. And last but not the least, my hello, yeah, my professor, it's a Tapas Bhattacharya, who taught us global tectonics means in our master's degree in Calcutta University. I am also in debt to his dedication. Otherwise means this day would not have been possible, because I was actually motivated in structural geology and global tectonics by he means his will of teaching global tectonics. So that's why I have been motivated by him. So I think that's enough. It's a very long lecture. I think many of you have many questions, so I'll now try to answer your questions. Let's have a blank slide.
Thank you, sir, for thank you, sir, for such an informative and marvelous session. We learned a lot from this session. So, dear participants, whoever has questions, kindly put up one by one. Sir will answer them.
Any participants who wants to ask any question, he or she can unmute themselves.
Hello, sir.
Hello, yeah.
Sir, you have explained about Bobbitt triple junction. Can you please explain again how it is RFF?
Okay, this I'll go to this one. Yeah, this one actually, the thing is that this triple junction has been formed by the means intersection of this ridge, that is South Atlantic ridge, that is the southern part of the mid Atlantic ridge system. This is the mid Atlantic ridge here, okay, and this is the southern part, so we can call it South Atlantic ridge, this part. And actually there are two ridges. One is the Southwest Indian ridge, this one, and there is another South American ridge, this one. They are also coming in this direction like this one, and this one. But the thing is that always ridge systems are always dissected by transform faults like this one. Yeah. So if you look at this one here, yeah, right, this one, that if there is a mid oceanic ridge system like this, then there are always transform faults running like this, running like this. So they are at many places they are dissected by transform faults to actually accommodate the relative motions, because somewhere the motion is higher, like I just yeah shown you over here, that somewhere the motion is comparatively higher, somewhere the motion is comparatively lower. So to actually accommodate this change in the motion just along the ridge, here also you can see the motion along the ridge is changing from 18 to 25 to 35, but the ridge is actually the same ridge. So to accommodate this change in the means velocity of the spreading ridges, you need transform faults. So these three ridges are also dissected by a number of transform fault. Luckily this part, the South Atlantic ridge part, has not been dissected here by any another transform fault, but in case of this one, this is the fault that is actually dissecting this southwest Indian ridge, and there is another fault here that is actually dissecting the South American uh, ridge. So that's why it is forming and not a ridge. If there had been no means transform faults, then it would have been a ridge system. But as there are transform fault cutting this ridge, but not this one, so you are actually having a system of FFR, means this is a fault, transform fault, this is again a transform fault, and this one is a ridge. So here you have a triple plate junction of your fault ridge system, not ridge system.
Hey panic, my battery is
So
low.
this is mainly because of these transform faults that are actually changing the dynamics of this triple plate junction. If there had been no transform fault, then definitely it would have been a simple ridge system.
Okay, sir. Thank you, sir.
So, hello, sir.
Hello, yeah.
Hello, sir.
Yes,
Can you
sir.
explain the first numerical once more? Like, what are we supposed to do after finding the alpha? I could not get that.
Okay, let's go to this one. Yeah, after finding, let's rub it. Yeah. So from the simple trigonometric calculation, you have, for example, calculated this is 46 degree, and you already know the angle between this, because this ridge is trending 110, so the spreading will be perpendicular to this one. So if it is perpendicular to this one, then one end will be 020, another end will be 200, and you have the relative motion between your A and B in the direction east west like this. So 020 and 010 will give you 70 degree, so that's why it is 70 degree. Okay, now you have alpha of 46 degree with the east west line, so this is the east west line. So you will draw a 46 degree from here like this. So this is the direction of what? Direction of spreading. Okay, it is not the direction of the ridge or not the azimuth of the ridge, it is actually the direction of spreading. So this is your 46 degree line from east west, this is your 70, and this one will automatically become 64. Okay, so now your ridge will be always, like I earlier said, that ridge will be always perpendicular to the spreading, or the spreading rates will be always perpendicular to the ridge. Okay, and vice versa. So when you have this line already, then you can draw a perpendicular on this line to get the actual azimuth of the third ridge that was not defined earlier.
Okay, sir. Thank you.
Hello, sir.
Yeah. Go ahead.
Sir, I wanted to ask how can we decide which plate to keep in the stationary part in the velocity space? Is there any
No,
criteria?
first of no. Two, three criteria are definitely there. I have also mentioned those. But obviously, when you are referring to relative, it is not absolute motion. Obviously, these are all relative motion. So the first criteria, obviously, you can put in mind that if you have a trench like this, if you have a trench like this or a subduction zone like this, then it's better always to keep the overriding plate as fixed and to measure all the relative motion with respect to that overriding plate. Okay, but there is a fallacy that if you are considering, for example, plate A and C, then obviously you can keep the overriding plate. Sorry, I have written it in this direction. Sorry, this is the overriding plate, not the A, because the trench
Yes.
is okay. So this is a subducting plate. So when you are considering plate C and A, then you can keep your C plate fixed. Okay, but when you are considering, for example, your plate again C and B, you can also keep C as your fixed. But when you are considering A and B, the relative motion between A and B, then in that case it's better to keep B as your fixed. In that case you cannot or means consider this one as fixed. Again, this one is another trench. So the trench will be always fixed or attached with respect to the overriding plate always. So it's always the overriding plate is always better to keep it fixed. In case of when you are having a trench scenario, if means one margin is a trench, if none of the margin is a trench, for example all three are ridge system, then again you cannot keep directly one fixed, is always relative to one another. So you but definitely to do the calculation you have to start by considering, for example, you have A, you have B, you have C. So for uh, drawing the velocity space diagram, sorry, you have to start with the reference frame, and obviously you have to start, be it at this point, be it this point, you have to start with a point. For example, I have starting here with A, with respect to E I will put B, and obviously with respect to both of them I will put C somewhere here. Okay, so it's actually depends on your notion that means how you are drawing your velocity space diagram.
So we can take one plate as a stationary and then designate all the magnitude of vectors
Right,
according to
one
it.
plate you have to start, right, you have to start with some static condition, otherwise you cannot plot the relative velocity, because you need something static to plot the relative.
Yes, sir. Yes, sir. That's all. Yeah.
Sir, for the FTR case, this is unstable, you said. So, plate A move southwest for rifting, at the same time move northeast for subduction. So, for relative diagram, how we can say A move towards southwest, sir?
For this one, FTR, this is
FTR,
also
yes, sir.
FTR.
Yes, sir. Yes, sir. Yes, sir. This one.
Yeah, no, for this one, uh, see, when you are referring to the relative motion, you are actually considering one margin at a time. If you are considering about plate A, then A is moving towards the northeast direction like this with respect to C. If C, for example, I am holding C as static, then A plate is moving towards northeast like this, and A plate is also with respect to B now, with relative to B, A is moving towards east like this.
Yes,
But
sir.
so the relative motion of A with respect to B is easterly, the relative motion of A with respect to C is northeasterly, but the absolute definitely it is not possible to find out the absolute from this diagram. But if I consider the absolute, then if this is the center, then A is moving like this. Okay, so it is actually a combination of both the spreading as well as the subducting rate. So the more or less the motion will be something like this if I consider the absolute motion, something like this. It will be actually a joint component of both this spreading and the subduction. So more or less it will go something like this, because it will be influenced by both the spreading rate as well as the subduction rate. But we means it's always better to keep in mind that whenever we are considering or dealing with the stability of triple junction, we will also keep in mind that we are dealing with relative motion. We are not worried about absolute motion. So it is always relative to one another. So you can put relative to C, you can put it relative to B, but you cannot directly gauge the absolute motion from here. It's not possible. Yeah, for absolute motion actually you need means GPS positioning system and DGPS nowadays, differential global positioning system, and other things as well. So for that I think means you guys can ask Ashwini that how means plate motions can be determined from DGPS or GPS.
Sir,
Yeah.
can you define zipper shear zone in regional scale also rather than in local scale? Is it possible for us to do that?
It's actually quite hard because you have to trace, or rather you have to map the whole region for that whether there are shear zones coming and they are intersecting at a point or not. But before doing that you must have a fair idea that whether there is a possibility of getting a zipper shear zone or not. Means if you are working on a field, then you have got some field evidence of some zipper shear zones, then only you should be able to have a means idea that yes, regionally zipper shear zones can be possible. But otherwise just directly going in means into an area and directly starting to map an area without any prior knowledge or prior outcrop information, it is not possible to directly look into zipper shear zones. First you need to have some outcrop direct evidences, then only it would be actually helpful for you to map large scale zipper shear zones.
Okay, sir, can we say all stable triple shears, triple junctions in local scale are zipper shear zones?
Yeah, that is a possibility. Not much people have told anything directly about this, but yeah, I from my experience, from what I have read till now, regarding both triple junctions and zipper shear zones, it's possible that zipper shear zones are actually manifestation of regional scale triple plate junctions, you can say, or triple point, or triple you can also sometimes you can say that triple block junctions, that three blocks are coming in a zipper manner or in a manner like just we have seen for triple plates. Yeah, that's possible, but that has not been highlighted by any research till now.
Okay, thank you, sir. Got it. Yeah.
Hello, sir.
Yeah, hello.
Can you explain, sir, fault reach system again, sir? Fault F1, F2, F1, F2, and also reach combination. Can you open this slide?
Okay.
Yes, sir. Yes, sir. Oh, sir, this.
No, this one is actually the scenario of your fault, trench and ridge. So this one you are referring to, or you are asking about something else?
No, sir. Fault and ridge.
Fault and ridge. So yeah, fault and ridge, for example, that I was showing earlier. Yeah, fault. This actually there are two faults. This one is an example of a ridge, a fault and fault. So if I want to draw, let's have some space. Yeah. So this is a ridge in case this is a fault scenario. This is again a fault scenario. This is fault. This is fault. This is ridge. This is actually the example of your Bovet shear, means Bovet triple junction. So this is the South Atlantic ridge, and this fault is the fault dissecting the your southwestern Indian ridge, and this is the fault that dissects. Actually, there is a ridge going like this. There is a ridge going like this. Yeah. So this is the Antarctic plate. If I draw it, this is the Indian one. Yeah, this is not, sorry, this is not the Indian one, I'm sorry. This is the African one, this is the South American one. So this is the scenario at Bovet triple junction, where you have maybe possibly it was I don't know the exact history of this triple junction, but means it's possible that earlier it was a RRR junction. It's also possible, or that is also possible that in future it will become an RRR junction. But now the present situation, you have a ridge over here, you have a fault over here, you have a fault. This is South American plate, this is an African plate. This is the ridge between your Antarctic and South American plate. This is again the ridge between your African and Antarctic plate. So this is the scenario. So here, okay, let's have another blank slide. Yeah, for example, so you can draw something like this. Okay, and this is also ridge. So this is R, this is F, this is F. So this is RFF or FFR junction. Yeah, so what do you exactly want to know about this?
Sir, velocity figure of this fault ridge system. There was another slide where the velocity figure is drawn. Yes, sir.
For FFR, I don't think I have given that. This is RTF, this is RRR, this is TFF, FTR. No.
Yes, sir. Where
F1 and remember that
F1, F2, and there is two transform fault.
Yeah, transform fault. I am also showing you here. No, the Bovet triple junction. You have two transform faults, like this, and you have a ridge here. But I haven't shown any diagram. Okay, let's go to the means comprehensive diagram. For example, this one here. If you are referring to TTR, yeah, this one.
Yes.
No, you are referring to FFR. No, no TTR. FFR. Yeah, this one. Yeah, this one is an example of that. Means you can say the Bovet. Yeah. For this one, you have a fault going like this. You have a fault going like this, and you have a ridge like this. Yeah. So for this one, the velocity graph, velocity vector space will be like this only, A and B. So you can start with A. For example, you have drawn A over here. With respect to B, they are symmetrical because it's a ridge. This is ridge. This is fault. This is fault. So it will be a straight line like this, and the margin will be the perpendicular bisector along the ridge, like this. Okay, and then you have also the movement between A and C. A is moving towards southwest with yeah. Okay, so with respect to A and C, C is here, A is here. Again with respect to B and C, B is moving up. Sorry, C is moving up and B is moving down like this. So now you have the triangle, and always the faults will follow the velocity line. So these the faults are following the velocity line, but if you look carefully, they are not meeting exactly at a single points, but if they meet, then it will be stable, otherwise it is not stable. Like that they have already written in the book, that stable if C lies on AB, or if A, C, B, C form a straight line, otherwise it's not stable. So this was your
Okay.
question or something else?
Yes, sir. Yes, sir. Okay, sir. Thank you, sir.
Hello. Good afternoon, sir.
Hello. Yeah. Go ahead.
Can you hear me? Sir,
Yeah.
can a
Yeah.
can a stable triple junction point again become unstable in future? Like you have told us about the San Andreas fault. The present scenario
Yeah.
can be
Yeah.
again.
Right, definitely it's possible. It's possible. Definitely it's possible. That it depends on whether your subduction, for example, here the subduction in this case for San Andreas fault, here the subduction is actually going on between what? This ridge is actually subducted beneath the North American plate, this ridge, but someday it will come that this ridge will be subducted completely. Okay, so in that case, now the subduction will start of this transform fault. So obviously the dynamics of the triple plate junction may change. Definitely it may go from stable to unstable, and again it may become stable from unstable. So definitely it's possible.
Okay, sir. Thank you.
Hello, Don.
Yes, sir.
Yeah, means
Hello.
any more questions?
Hello, sir.
Yeah, hello. What?
Sir, what is the main difference between transform and transcurrent form? I face difficulties.
For that, you actually okay. Let me tell you in a very simple manner, but that is a completely a different lecture overall. But still, I'll show you something. So transform faults, when you are means referring to transform fault. Sorry, like this. Yeah. So in that case, if you have a fault like this, okay, so there is a movement like this and you have a movement like this. So in that case you can call it a transform fault, that your ridge is getting displaced in a sinistal manner, or it can also get displaced in a dextral manner. So the whole fault is actually, again, the whole fault is actually responsible for the movement or the means separation of the ridge. Okay, but in sometimes what happens, that actually differs in case of transform to current fault. Sometimes what happens, that if you have a ridge like this and again you have a ridge like this, so transform faults are very common, but in some cases what happens, that I already told you guys about the varied or differential. We have also seen from the global spreading rate diagram, that for example if the velocity here could be, for example, 10 degree, sorry, uh, 10 centimeter per year, here it could be 2 centimeter per year in each direction. Okay, so that is also possible. So sometimes what happens, this fault is initially a transform fault, and it has displaced the two parts of the same ridge into two ends, here and here. But now due to the differential rate of the movement of the mid oceanic ridges, here it is moving quite faster, here it is moving very slow. So though the overall direction of movement of this transform fault is sinistral, in parts like this one, we'll call it an active part, and these parts will call it an passive part. Passive part, why? Because there is no other movement apart from the overall movement. It is only this part are following the overall sinistral movement that is responsible for the whole transform fault. But when you are looking into this part only, this active part only, then the spreading of this one is quite higher with respect to the spreading of this. For example, this is 2, this is 10. So in this active part, what will happen? The mid oceanic ridge basalt will try to flow here in a faster way, and obviously here in a slower way comparatively. So in this part only it will give you a dextral kind of spreading, or a dextral kind of motion to be specific. So in transcurrent fault you always have an active part and passive part, and this active part is generally will give you a different kind of motion with respect to the passive parts. But in case of simple transform faults, the whole fault will only give you one direction only. For example, like this, nothing else. So that is the basic difference you can say about transform and transcurrent fault.
Okay, sir. Thank you.
So, any more questions from anyone? Any questions from anyone? Anyone? Sir, I guess. Hello, sir. Am I audible?
Yeah. Go ahead. Yeah, go ahead.
I guess no more questions left. So thank you, sir, for such an informative session, for answering so many questions, and hope we get you every time when we seek any help in structural geology and plate tectonics in near future.
Yeah. Definitely.
Thank you so very much.
Yeah. Okay.
Have a nice day, sir. Dear participants, next session of Ashwani Raju sir will be starting sharp at 3 p.m. and not at 3:30 p.m. I repeat, next session of Ashwani Raju sir will start sharply at 3 p.m. So kindly join on time so that you we may miss nothing. It's going to be very interesting session in continuation to the session that we had yesterday. So, I request you to please join at 3 till and if anyone has any questions left that network issues or anything or could not ask here just now, can mail to us. We'll forward that mail to our teachers, and then once they answer, we'll definitely get back to you. So thank you very much.
मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी ये तीनों लोकों से न्यारी काशी सुज्ञान धर्म और सत्य राशि बसी है गंगा के रम्य तट पर ये सर्व विद्या की राजधानी की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य सुंदर। रचे है विद्या के भव्य मंदिर, ये सर्व सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि। बसी है गंगा के रम्य तट पर, ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य सुंदर। है विद्या के भव्य मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या। अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि। बसी है गंगा के रम्य तट पर, ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य सुंदर। रचे है विद्या के भव्य मंदिर, ये सर्व सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि। बसी है गंगा के रम्य तट पर, ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व वेद्या की राजधानी राजधानी। मनोहर अतीव सुंदर ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी सुज्ञान धर्म और सत्य राशि बसी है गंगा के रम्य तट पर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर है विश्वकर्मा का कार्य सुंदर रचे है वेद्या। सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी सुज्ञान धर्म और सत्य राशि बसी है गंगा के रम्य तट पर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर है विश्वकर्मा का कार्य सुंदर रचे है वेद्या के भव्य मंदिर ये सर्व सृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। अतीव सुंदर ये सर्व राजधानी राजधानी। ये तीनों लोकों से न्यारी काशी सुज्ञान धर्म और सत्य राशि
Hello, Atu. I am audible to you.
के रम्य तट पर ये सर्व वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्व वेद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर है विश्वकर्मा का कार्य सुंदर रचे है वेद्या के भव्य मंदिर।
Good afternoon, sir. Sir has joined, I guess.
No. Sir is not joined yet. Yeah, sir is requesting. Right. Sir is joined.
Good afternoon, sir.
Good afternoon, sir. गुड आफ्टरनून बोल रहा है. शुरू करना है. हाँ शुरू करें. हाँ सबको. हेलो.
I wish you very good afternoon, sir. So shall we start today's evening?
Hello.
Sir, shall we start?
Yeah. We shall start. We shall start without wasting any further time. Thank you very much.
So, dear participants, we are starting our evening session, Fundamentals of Remote Sensing by Dr. Ashwani Raju, sir, which will be in continuation with the session that we had yesterday. Hope we all enjoy this. All the best. Sir.
Okay, thank you, Don. Okay, guys, slide is visible to everyone.
Yes, sir.
Yes, sir.
Not yet, sir.
Okay, now slide is visible to everyone, or is there any problem? Okay.
Yes,
okay.
Yes. So, but it will be better if you get it a full screen, PowerPoint mode. Get a full PowerPoint.
Okay, it's already open in full screen mode. I think it will take some time, and
then we shall start and let's see during this session it will become okay.
Okay, or if there is any problem, if Soham is there, he will change the slide if he's there.
shall
शिवम तो अपना स्क्रीन शेयर कर दो एक काम में.
So I think now it's visible. We should proceed. Without any further delay.
Okay. Hello everyone. Hope you all have enjoyed yesterday lecture. So we shall continue from the last slide from tomorrow. Okay, in case if anybody is having any problem, they will definitely ask, or is there any problem, anyone? Hello, am I audible to everyone?
Sir. Yes, sir.
Okay, is there any problem to everyone? They can ask, or we shall start now.
Start, sir, please.
Okay. So in last lecture we have already discussed about the basics of remote sensing
Hello, is anyone's mic is still on? Um, it's creating a lot of noise there. So okay, now it's good. Okay, so last lecture we have already discussed about the basics of remote sensing. The fundamental part is your wave, and based on the wave distribution, all the satellite sensors have been designed and work together. Right, so we have already discussed about this FCC. We have discussed a little bit about the things, and now we're going to continue from the FCC to the resolution in the remote sensing. So resolution in remote sensing is nothing but these are the potential details which are available within the satellite system or within the data, based on which you go and select the data of your use. Right, based on these feature, based on these potential detail, you are going to you able to select the kind of data you like. Right, for example, if somebody is want to use structural geological mapping of the area, then he or may she go and try to download the cartosat data or high resolution any data. Right, so resolution in remote sensing is basically what they do. They actually provide you the opportunity based on which you're going to select your data. Right, so specifically the resolution in this remote sensing has been divided into four parts. One is the spatial resolution, another one is the spectral, then we have a temporal resolution, and finally we have a radiometric resolution. So if you see the spatial resolution of a satellite data is nothing but a size of a pixel. Right, whatever the size of one pixel with respect to the ground truth is called as the spatial resolution of a particular satellite sensor. Right, and spatial resolution of a satellite sensor is provided the instant of a particular ground segment, area of a unit area of a particular ground segment. For example, take an example of a Landsat panchromatic data. Now I believe you already know that what is panchromatic. Right, so panchromatic is nothing but a photograph or satellite image which has been taken in a range of 0.35 to 0.75 micrometer wavelength region. So size of a pixel is, for example, take an example of the Landsat panchromatic data has a size of approximately 15 meter by 15 meter on the ground level. That means the image is having a spatial resolution of 15 meter by 15 meter. So it is nothing but a size of a pixel, and this size is actually representing the instant which has been sensed by a particular scanner of a satellite. All right, and it is also called as the ground resolution element, GRE. It is sometimes also called as ground resolution element. Okay, so next is, for example, if you see this particular figure, you have different type of figure of a particular area, ranges from 1 meter per pixel, 2 meter per pixel, and goes up to the 30 meter per pixel. Right. So if you see closely, 1 meter per pixel image is much better to identify the feature as compared to the 30 meter per pixel. Right. So spatial resolution is basically the size of the pixel. As much as smaller the size of the pixel, your feature or your object would be very much clear in the satellite data. So that is why spatial resolution is very much important. So for example, if anybody was to do some land use land cover mapping, or somebody want to use structural mapping, or want to see the structure, then high spatial resolution data, that means 1 meter per pixel data is
Sorry
quite
to
useful.
interrupt. Kindly please wait for a second. The PPT is getting loaded.
Okay, I'll wait.
वो लगा रहे आया नहीं
Is the screen visible, sir? Sir, please unmute yourself.
Give it to full screen mode.
Okay, sir. Is it visible?
It is visible, but it is not available in full screen mode. That is the problem. Yeah, now it is good.
Okay, sir. Thank you.
So I tell you, you just change the slide. Okay.
Okay, sir.
Okay. So spatial resolution, as we have discussed, it's nothing but a size of the smallest object or size of a pixel, and it is sometimes also called as a ground resolution element, right? And it represent the segment or a particular instantaneous field of view of the particular object on the surface of the earth. So if you see the figure, change the slide. Okay, if you see the figure, we are comparing a different resolution of a satellite data, right, with respect to other satellite data. So for example, on the left hand side, the topmost image, if you see, it is having the spatial resolution of 1 meter per pixel. The size of a pixel is 1 meter by 1 meter. And if you see closely, that 1 meter by 1 meter pixel is the features are quite good, able to recognize in 1 meter by 1 meter pixel as compared to the 30 meter by 30 meter per pixel area. So that is how spatial resolution play a useful role in the identification of the particular object, right? So take an example. For example, if somebody wants to do mapping, right, and try to identify the features, structural feature, then he or she would go to the 1 meter per pixel area, right, and where the features are quite prominently identified. Okay, come to the spectral resolution. Change the slide. Yeah, so if you see the spectral resolution, we all know that the mean of the spectra or the meaning of the spectra is particularly we are talking about the wavelength region, right? So whenever I tell you spectra or spectral region or wavelength region or channel or band, all these that means that we are continuously talking about the wavelength region, right? So a spectral resolution of a particular satellite data, that it referred to the width and the number of the spectral band, that is number of the photographs or number of images are taken in a particular wavelength channel. Take an example of the Landsat. For example, Landsat data is having is a multispectral data, or Landsat ETM plus is having 7 bands, ranges from 1 to 7, right? That means each images or each band or photograph or image has been sensed or recorded in a particular wavelength region, right? So wavelength region are number of the total wavelength region in Landsat is 7. So that is the spectral resolution of the Landsat data is 7. For example, if I talk about the hyperspectral data, hyper it means that the number of spectra or number of bands or number of channel are more than 220. That is why it is called as a hyperspectral. For example, if number of spectra is more than 2 or 3, then it is called as a multispectral, right? So spectral resolution is very much important, and closer the spectral resolution of a or wavelength channel, you can identify the closest or the very much related particular objects, right? So that is why your spectral resolution is very much important. So spatial resolution is nothing but deal with the size of the pixel. Less the size, you can prominently identify the feature, and spectral resolution is the number of wavelength channel recorded or used by a particular sensor to record the certain object, right? If the number of channels are good, then or quite in high number, then even the minor differences you can between the object you can determine, right? And that is how your spectral resolution is very much important. So Landsat data or Sentinel data or your Astral data, all these are the multispectral data. They take the response of a particular object or the ground in 7 channel or 12 channel or 14 channel, But hyperspectral data, if you consider, then hyperspectral data take the response or measure the response in more than 220 channel, so that you can better identify the difference between the particular two objects which are closely related, right? So if you see this figure, change the next slide. If you see the particular figure, this figure is showing showing the comparison between the different satellite sensors. So if you see in the right hand side corner, we have the Aster and the MODIS. So these Aster and the MODIS capture the data in 5 or 6 or multispectral bands, and Landsat OLI or Sentinel or other data, they used to capture the information in majorly information in the visible or near infrared region of the spectrum. So number of channel, as the number of channel has been increases, the resolution or spectral resolution of a particular data also increases, right? Change the next slide. If you see the next photograph, you can easily understand what is the spectral resolution. So in low resolution data, only single band is there, right? That ranges from 0.4 micrometer to 0.7 micrometer. But if you see the high resolution data, that whole 0.4 to 0.7 meter resolution data has been divided further into 3 channels. So high resolution can only be called as when the number of channels are more, and low resolution has been called as when number of channels are quite less in number. Okay. Now coming to the temporal resolution, change the next slide. Temporal resolution is nothing but it is basically the frequency at which the images are recorded, right? It is also called as that means at how much time interval a particular data has been repeatedly passed from a particular area over the surface of the earth, right? And that is called as a frequency. Take an example of a Landsat data. For example, Landsat data has the revisit time of approximately 8 to 9 days. That means every 8 days Landsat satellite has been passed over the same surface, same point over the surface, right? And temporal resolution data is very much useful when we are dealing with data analysis, right? Time series, that means if you want to see the change with respect to time, then the temporal resolution of the data is very, very much important. For example, if you take the example of a flooded river, for example, now these days are the rainy season, and every more or less every river has been overtop its bank. So if you want to see the how the flood has been progressive or it captured the particular area, then you can use the time series data, and it will give you information has been flooded during the what interval of time, right? So that information may be particularly very useful in case you want to do some risk management related to the flood. All right. So this is how your temporal resolution has been very, very much important.
Sir, sorry to interrupt. I want to ask a question. So, as we study new tectonics, where per year centimeter scale movement are recorded, so these Landsat can be used there.
You can use Landsat for different purposes. Let's talk about, you are talking about the movement, right? You are talking about the movement, at what rate a particular landslide is occurring, what particular mass has been moved within a certain interval of time, or subsidence has been occurred within a particular interval of time, right? So if you talk about the movement, then you have to use not Landsat. Landsat is optical data. Then you have to use the microwave data, which is particularly useful for the analysis of movement related features, right? For example, movement of the glacier you can be recorded, or you can analyze the rate using the microwave data. Take an example. For example, I give you one example related to the groundwater. Now these days, groundwater related problem is everywhere, right? Population is continuously, exponentially is increasing, and that increased population is put at a continuous stress over the groundwater, right? So more the population, the extraction of the groundwater is much more. So when the extraction of the groundwater is much more, what happened that the cohesion between the aquifer, sandy aquifer, what happened that cohesion has been decreases, and because of the decrease in cohesion, the land has been subsidized. All right, so subsidence has been occurred. Right, so that problem has been recognized by a very good, in a potentially recognized using the temporal microwave data set. Right, one study has been published in 2012 in central Mexico, where a large area has been subsidized because of the exponential groundwater exploration. Right, extraction of the groundwater in central Mexico. One city is there in central Mexico that has been subsidized. A certain area of that city has been subsidized because of the over extraction of the groundwater. So that over extraction of the groundwater, how much at how much rate, what is the rate of the subsidence, that has been detected by the time series microwave data. Right, so you cannot use the land set data, but you can use microwave data for the analysis of these kind of features, right, for movement related features. Okay, if anybody is having problem, they can ask. Am I audible to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, come to next slide, which is radiometric resolution. Okay, so radiometric resolution is basically determine the sensitivity of a sensor to measure the magnitude or response of electromagnetic energy. Right, it is basically that what energy is required at how much energy a particular sensor has quantized the information. That is called as a radiometric resolution. And finer the radiometric resolution, more sensitivity of a particular senses has been increased for a particular object. Right, change the next slide. If you see the figure, right, if you see the figure, the sensor has measured the radiance or reflected radiance at 8-bit quantized level. Right, 8-bit, that means 2 to the power 8. So the tone of the pixel has ranged from 0 to 255. 2 to the power 8 is equal to 256. That means if we convert this 256 into the range of value, then it ranges from 0 to 255. Right, so 0 represent completely black and 255 represent completely white color pixels. Right, that means if a value of a certain pixel has 255 or 250, that means it is almost capturing every whatever reflection has been made, it capture almost a reflection. Right, if the reflectance is high, it captures the entire reflectance, and the value is approximately 255. If there is complete absorption takes place by a certain object, there is no emitted radiance, so there is no reflected radiance, and the pixel value it has is 0. Right, so for example, in 8-bit level, you can have the digital number value ranges from 0 to 255. Right, if you see the left hand side figure, the particular images or a band 1, 2, 3 has been divided further into the rows and the columns. Right, in a Cartesian coordinate system, in the rows and column it has been divided, and each pixel, each square box is representing 1 pixel. It is the IFOV, and each pixel has been, the object has been defined by a number, and that number has been defined by its quantized value or 8-bit value or 12-bit value. Right, so if a particular photograph has been taken in 8-bit resolution, that means within the whole image the color has been ranges from 0 to 255. That means completely black to completely white in a grayscale image. Right, if for example, if we have, if a data has been taken in 12-bit resolution, then the value has been ranges from 2 to the power 12, that means 4096. Right, so minimum value is 0 and maximum value is 4096. So whenever you are increasing the range from 255 to 4096, then definitely you would be able to recognize the more information you able to recognize. Right, that is why this radiometric resolution is quite useful. I am giving you an example. For example, take an example of ASTER data. Right, ASTER is Advanced Spaceborne Thermal Emission Radiometer, and it has 5 thermal bands. Right, that means 5 images have been taken in thermal infrared region of the spectrum. So that 5 images has been taken in 12-bit resolution. That means in every band the color value or grayscale value has been ranges from 0 to 4096 value. Right, And if we convert these 4096 values to a temperature values or degree Celsius value, you will able to find out that the temperature of the particular pixel or pixel integrated temperature has been much finely recognized in 12-bit data as compared to 8-bit data, right? And that is why this radiometric resolution is quite useful. In Landsat 8 we have a thermal band, in Landsat 7 ATM plus we have a thermal band. That thermal band is approximately 8-bit data, right? So value of the temperature ranges from 2 or determined from 0 to 255 values. But in case of the Aster data, temperature has been recognized from 0 to 4096 values. So in Aster data, you can able to identify major or even the minor differences in the temperature variation as compared to the Landsat data. And that is why this radiometric resolution has been much useful, because higher the radiometric resolution, much finer detail has been recognized. All right. Understand?
Yes, sir.
Okay, come to the next slide. Next slide. Okay, come to slide number 53. Okay, if you see this particular image, right, upside image is taken in a 2-bit radiometric resolution, right? 2-bit radiometric resolution, that means values are 0 to 2 to the power 2, that is 4. Values are ranges from 0 to 1, 2, 3 and 4, right? So if you see that above image, you can find out that the values are only, or grayscale values are only ranges from 0 to 4 or 0 to 3. But in case of the lower image, which has been data has been taken in 8-bit resolution, radiometric resolution, then your grayscale values has been divided into 0 to 255. So more finer detail has been recognized in the 8-bit data as compared to the 2-bit data. If you use the 12-bit data, definitely it has more prominently determine the objects as compared to the 2-bit data or 8-bit data. So that is how your radiometric resolution plays a very important role when you are going for your objective of any objective, right? And specifically this radiometric resolution is very, very much important if you are trying to detect the thermal phenomena. For example, anything which is related to the high temperature variation, then this radiometric resolution has to be very, very much important. So far we have discussed about the resolution. If you have any problem related to the resolution, you can ask your questions. Hello, am I audible to everyone?
Yes, sir.
Yes, sir.
Yes.
Sir, I have a question. Why can't we use highest radiometric resolution type sensing all the time in satellites?
Actually, the problem is, I tell you the problem. Sensor, if you see, or if you take the data from, for example, Landsat, you take the example of that 8-bit resolution, you take the Aster data 12-bit resolution, or many more resolution is also there. The problem is when you try to quantize the energy which is using the region, using the larger wavelength region. For example, that thermal data in the Aster, within the Aster, thermal approximately 100 by meter है 100 meter, but the data has been taken in 12-bit resolution. The problem is if the sensor is tried to quantize the energy of higher wavelength region or the larger wavelength region, it takes more energy to that convert into the image, right? So when it take it require a larger amount of energy to change the digital information to a image information, right? So when you do this, your pixel, the size of the pixel has been increases. So if you see the 12-bit resolution data, the size of the pixel is quite much, right? That is the problem. You can use it every time, 12-bit data can be used every time, but the problem is then the pixel size has become very, very much larger, right? And when the size of the pixel is become larger, for example 100 by 100 meter, you are not able to recognize the object easily, right? And that is why these phenomena have been used in thermal remote sensing, not in microwave or not in optical remote sensing, because if you use a 12-bit data in optical remote sensing, then you require a very large amount of energy to change it into a digital format, and you require large amount of energy, then the size of the pixel is that much energy is not available. So if you do that, then a high amount of energy is required, and ultimately size of the pixel become very small. Or if you use the low energy, then the size of the pixel is very much larger. So when the size of the pixel is become larger, you can't recognize any object, right? So that is why radiometric resolution is important, but ultimately it depends upon the user what type of data he or she may require, yeah, or interpret. That is the thing. You can use every time 12-bit radiometric resolution, but the problem is then in that case the size of the pixel has been increases, and you can't able to differentiate between the different objects. That is the problem. Okay.
Yes, sir. Thank you.
Okay. Okay. Any more question if somebody was asking? Yeah.
Sir, I could not understand the radiometric resolution. Can you please explain once again?
I am telling sensor has installed or onboard with the right or onboard with it is actually try to quantize the energy, right? Whatever reflected response or emitted response we are getting, sensor is try to quantize it in a 8-bit level or 12-bit level, right? For example, if it quantize the energy or response in 8-bit level, then you only have value that is ranges from 0 to 255, right? You can get the single band image, and single band image is a grayscale image. So the tone of the gray color has been ranges from 0 to 255, right? And 255 represent completely white pixel, and 0 represent completely black pixel. Up to this point, is it clear? Hello?
Yes, sir.
Okay. So if you are using 8-bit data, that means 8-bit, that means 2 to the power 8, that value become 256. So if you take the whole range from 0, then it range from 0 to 255, right? So your digital number value is the value of a pixel, is the numerical value of a pixel. So that numerical value of a pixel has been ranges from 0 to 255, right, in a gray scale, where 0 represent completely black and 255 represent completely white pixel, right? So this is called as the radiometric resolution. That means sensor capture the response of a particular object in a quantized level, right, in 8-bit quantized level, right? वो उसको 8-bit के quantized level में ही energy के response को capture करता है. If you use the 12-bit resolution, then the range would be increases from 0 to 4096. So when you get the 4096 values, automatically you will be able to determine the closest difference also, right? That is a difference between 8-bit data and 12-bit data. So if you use the 12-bit data, the quantized level or quantization level is quite much high, and you able to differentiate the minor difference within the close object also, right? That is called as a radiometric resolution. Is it clear?
Yes, sir. Thank you, sir.
If not clear, I can repeat it again. There is absolutely no problem.
Sir, I got this point. Thank you, sir.
Okay. Come to the remote sensing data set. Next slide. Come to the remote sensing data set. Okay. Now, so far we have discussed about electromagnetic wavelength radiation. We have discussed about the resolution. We have discussed about the color combination, type of sensor. Everything we have discussed, right? But now again, as we are the user of the remote sensing data set, the problem is how to download this data and from where we can get this particular data, right? So now these days there are almost everywhere where the good remote sensing agencies are all over the world. They are providing data free of cost, right? And the purpose of it, they just want to increase the scientific contribution in the field of remote sensing, right? So we will so far discuss about what type of data remote sensing data sets are available, and particularly what is the use of a particular data and from where you can get that particular data and what level of the data for your purposes, right? Change the next slide. No, earlier one. First is earlier one. It's slide number 55. Right. Okay. So if you see that on the left hand side, we have a different type of the remote sensing data sets, right? We have a multispectral data set. You all know that multispectral is when the photograph or the image has been taken in a more than 2 wavelength region, right? That is called as a multispectral. It is called as a hyperspectral if the photograph or image has been taken in a more than 220 channels. And then the thermal remote sensing if the photograph or image has been taken in a thermal infrared region. And then if the photograph has been taken in a microwave region of the spectrum, that means from 1 millimeter to 1 meter wavelength region, then it is called as a microwave remote sensing. And every type of remote sensing have different type of the data sets which are freely available in the market, right? So for the multispectral data set, particularly multispectral data sets is quite useful for land use, land cover, change detection kind of thing, for the structural mapping or identify the features. For these kind of things, multispectral data sets are very important. For the vegetation purposes, for the natural hazard assessment, these multispectral data sets are important. So this resource set data, resource set 1 is IRS, I think IRS 1D list for MX data is the resource set data, and this data is provided by the ISRO, right? So this is data is available free of cost, and it has having the resolution, spectral spatial resolution is approximately 5.8 meter. The size of the pixel is approximately 5.8 meter by 5.8. I don't know whether it is free or not, but it is provided by the NRS, National Remote Sensing Center, Hyderabad. Then we have a Cartosat data, Cartosat 1, it has the resolution of 25 centimeter by 25 centimeter, 2.5 meter by 2.5 meter. That data is also available at approximately 1400 rupees or something. One scene is approximately 1400 rupees or 1600 rupees. It is cheap, and if you are a student, you will get that particular scene in approximately 800 or something, or maybe more. I don't know the exact the value of the data. Then Landsat 8 OLI, this is the recent Landsat data. It is available free of cost at very high temporal resolution. Then we have a Aster data. This is also available free of cost, but I think after 2017 that Aster data has been decommissioned. Its thermal band or shortwave infrared band has been decommissioned from 21st March 2017, I think, or 2011, whatever. Then we have a Sentinel-1 data. Not Sentinel-1, it's Sentinel-2. So Sentinel-2 data is also available free of cost. Then if you want to do hyperspectral remote sensing is particularly very much important. If you want to use that hyperspectral data, you can download it from the Earth Explorer, and the Hyperion data is very good, right? So it has more than 220 bands. Then in Chandrayaan 1, this moon mineralogical mapper is also there. If somebody wants to use the Chandrayaan data, they can download it from the NRSC website. Then in the thermal remote sensing, lot of satellites data available. For example, Landsat OLI also has a thermal band, which is called as a thermal TIRS, thermal infrared remote sensing. Then we also have Aster thermal infrared data. We have a MODIS data, but the resolution, the spatial resolution, the size of the pixel in case of the thermal remote sensing is quite much larger. Then now these days, microwave remote sensing data is quite potentially used by the different remote sensing people of the remote sensing. And this LOS pulsar data, radar set data. LOS pulsar data is free of cost, radar set is costly, and TerraSyrex is extremely costly. One scene is approximately 4,50,000 rupees. And this NV set data and Sentinel data is available free of cost, right? So based on your purposes, whatever is your purpose, you can go and download this type of data, and the processing of these data is also different based on your purposes. So next slide. Okay, now the question arises from where we can download this data, or how to identify it. So rho is nothing but a longitudinal points, and the path is nothing but a orbit of the satellite, orbital path of a satellite. So annotation wise, if you want to use, if somebody have the path and rho, they can directly go to the website and put it the value of path and rho, and they can easily download the images. So annotation wise, if you see, it has been written as 127-043. So 127 is basically the path number, that is the orbital number, and 043 is the basically the longitudinal number. So next slide. Okay, if you see that particular figure, you can see that there is in greenish path, that is the orbital path of a satellite, and this red color is basically representing the longitudinal line of frame, right? So these are called as a row number. So if somebody want to download, depending upon the path and row indexing system, they used to find out the path and row number, and they give an input to the website, and ultimately they can download the data using the path row system, right? So, and if the path row system is not available,
Sorry to interrupt, sir. Can you please read the diagram? The blue one is longitudinal path.
No, blue one is the orbital path. Blue one is the orbital path, that is the descending orbital path. This is the path of the satellite in which it is rotating, right? And these red one are the longitudinal point of line of frame. These are the longitudinal. Based on that, these can recognize. All right.
Thank you, sir.
Okay, so if most of us don't able to recognize the path and row indexing system, then there is another option is available. If you know the coordinates of your area, you can directly give the input of your longitude and latitude of your area, and you can immediately download your data. So data, next slide. So data can be downloaded from the various agencies. Various agencies has provided the data, right? And quite pioneer one is USGS, right? So there is one website which is Earth Explorer, right? So earthexplorer.gov.in. You can go to the Earth Explorer and you can download the raster dataset, for example, Landsat dataset, Sentinel-2 dataset, ASTER dataset, digital elevation model. All these data can be downloaded from the Earth Explorer site. You just have to go there and sign up yourself, and just you can put your path or row number, or you give the shapefile of your area, or you give the coordinate system of your area, coordinates of your area, and you can able to download whatever data you would like to download, right? Apart from that, if we see the Indian platform, in Indian platform we have a Bhuvan, right? So on Bhuvan, lot of thematic map or the thematic layers are given, right? If somebody want to use the vector layer, they can use the vector layer. They can easily go there and easily download the vector layer. So geomorphology, lineament, and other type of layers are that. You can go to the Bhuvan website and you can download the IRS series dataset. I think IRS 6 dataset is free to cost, and Cartosat DEM is free of cost. So you can visit to the Bhuvan website and you can download data. Apart from that, this Earth data is there. Earth data you can go to this website to download microwave data, and you can go to the European Space Agency, ESA, European Space Agency. You can also go there and you can download the microwave data set, right? So these are the various agencies from where you can go and you download your data set free of cost. Only just you need to sign up your things, detail. Okay, next slide.
Sir, excuse me, sir. Sorry for the interruption. We have received a question.
Yeah.
Swastik, MSc first year, BHU. What is rate of resolution in remote sensing?
What is?
Rate of resolution in remote sensing.
What is what? See, let me see the question. Rate of resolution. I think this trade-off resolution, I really listened to that particular term for the first time. If you have some idea, you can give me a little bit of idea. I'll try to see that thing. If you have any option or if you
okay, sir. Then Swastik might again reciprocate what you want actually.
Okay. So maybe I think this may be of or a type of this, any type of resolution we have discussed is not more than that. Or if you have any more detail about it, you can just type it down and I'll try to answer your question.
Continue, sir. Hope
Okay.
he has got his answer, or he will kind of soon.
Okay. So, okay, where were we? Okay. So if you see that, is there any question? Okay. Okay, so if you see that particular site, this is the user platform for the Bhuvan website, right? And on the right hand side, you have shown the Cartoset dataset. I think it is Cartoset. Okay, it is basically a shape of the particular satellite. So all over the India, the data are available. You can go and register to these platform, and you can even download your data. Right. Come to next slide. So this is the Earth Explorer website, right? And if you want to go, you go to the Earth Explorer website, and you put on the left hand side, you can see the I think what come to next slide. Yeah. So if you this is the platform of this Earth Explorer website. On the left hand side, you can see that there is a lot of options are there. You need to fill that parameter, and ultimately you can reach to your area. So what you need to do, you just need to put your coordinate system or coordinate area of your coordinates. Then you can able to download or recognize what type of data you would like to download. Then another one is the Alaska satellite facility. Now these days people are quite using these things. Alaska satellite facility that provide this microwave data, that Sentinel-1 microwave data that provide for any purposes of your use. For example, if somebody wants to see the landslide movement, or somebody wants to take the glacier movement, or something like that, you can go to this website and download the microwave data. That data is Sentinel-2. Okay, next slide. Okay, again, this is another platform which is Earth Data. It is very much similar to the Earth Explorer and another thing. So whatever data you want to download, only thing you need to explore these website. Every sort of data is available over there. Right. Again, come to next slide. Okay, next. Yeah. So this is we will try to discuss about some of the very frequently used freely available data. One of the data is the Landsat, and Landsat has been launched in 1973 and is still working, and it has been launched up to the level of 8. 1, 2, 3, 6, not 6. I think 6 has been lost. 5, 7, and 8. Right. So now these Landsat 8 OLI, Operation Land Imager, is already working, and if you want to download, you can download these. So this has a specification has been given of the Landsat multispectral system from what type of enhancement they have done from Landsat 1 to 3 and Landsat 4 to 5. So specification has been given band wise and the wavelength wise, and spatial resolution, that means the size of the pixel has been also there. So if you see from Landsat 4 to 5, they have maintained the spatial resolution of 60 meter by 60 meter, and now in Landsat 7, the spectral resolution or the spatial resolution has been ranges from 30 meter to 30 meter, 30 meter by 30 meter, and its panchromatic data is having the spatial resolution of 15 meter by 15 meter. So that data is freely available, although it is moderately spatially resolution data, but it is available at quite for a quite frequently used and high temporal resolution. That data is available. You can use at any time. So it has a revisit time of approximately 8 days or I think 16 days. and every 8 days it has repeated its own path. So that data is frequently available. You can download this data from Earth Explorer website. Next. Okay, so this is Landsat operational land imager. This is Landsat 8 OLI. Alright, so this now these days Landsat 8 is in currently operation. So the data is available free of cost and you can download from Earth data. Then again in the next slide we can see the comparison between the Landsat 7 and Landsat 8, right? So if you see that in Landsat 7 they have band number 6 thermal infrared, right? And if you see that in the pixel resolution they have given 30 meter and 60 meter, 30 meter or 60 meter. So that means at 60 meter resolution data is their original data, and they are now providing the 30 meter resolution data as a resample data, right? So resample, we will further discuss what is resample, right? It's come in the further slides, so we'll discuss what is resample, right? So in band number 6 in Landsat 7 they have given only one single thermal infrared region, and in Landsat 8 they have provided the two thermal infrared region, right? TIRS1 and TIRS2 both have, I think, the resolution of approximately 100 meter by 100 meter, right? Only difference is that in band number 6 in Landsat 7 the resolution is, I think, 8-bit, but in case of the Landsat 8 the radiometric resolution is, I think, 12-bit, right? And potentially they are more providing 2 more bands to you, right? Apart from that, in Landsat 8 one coastal band is also there, one Cirrus band is also there for the atmospheric monitoring, right? So this is the potential upgradation in the Landsat 8 from Landsat 7. Okay, next slide. Next. Okay, so this is another very good data which is called as a ASTER, Advanced Spacebound Thermal Emission Reflection Radiometer, right? So if you see the ASTER has number of band, approximately 15 number of bands are there, right? And it has 5 bands in thermal infrared region and approximately 6 bands in shortwave infrared region, right? So this shortwave infrared region is particularly very much useful for the lithological discrimination, for the geology purposes, right? And this thermal infrared region is quite useful for for measuring or for determining the thermal phenomena. And you can see that TI band is also available at a 16-bit resolution. So if you use ASTER in comparison of the Landsat, you can able to identify even the minor differences in the temperature of a pixel. You can able to identify in the ASTER as compared to the Landsat, right? More the resolution of the ASTER is also 90 meter as compared to available. Okay, next.
Sir?
Yes.
So I wanted to ask that Landsat data set has 2 components. One is MSS, and one is thematic mapper. And what are these actually?
MSS is the name of the sensor. MSS is multispectral sensor, right? And TM is the thematic mapper. If you go in Landsat 7, it becomes ETM plus, enhanced thematic mapper plus. And similarly, if you go to Landsat 8, it becomes Landsat 8, Landsat 8 OLI, operational land imaging system, right? So these are the name of the sensor. This MSS is the multispectral sensor and TM is the thematic mapper. So earlier this Landsat in 1973 was launched with only 4 bands, right? 1, 2, 3 and 4 bands. So as the number of band is basically more than 2, so that is why they have called as multispectral sensor, right? And when they have launched Landsat 4 or 5, then they have increases the spectral range of spectral resolution of the Landsat data. So they have called it as thematic mapper. So thematic mapper, TM and MSS, all these are the name of the sensor within the Landsat satellite. So Landsat is a satellite, MSS, TM is the name of the sensor. Okay.
Okay, sir. Thank you.
Okay. Okay. So data type and specification. One more thing, if you go and try to download the data, for example, if you want to download the Landsat data and ESTA data, then these data are provided in a different level. For example, level 1T, right? So level 1T, if you see that level 1T is I think level 1 data, and which is T is terrain corrected. So we will discuss later about the corrections. So T is stand for terrain corrected. That means whatever error has been occur in the satellite sensor because of the change in the elevation of the terrain, that data which they have provided is automatically corrected data they are providing. They are providing corrected data without any topographical error. So level 1T is the terrain corrected data, and that data is available in 50 meter, 15 meter, 30 meter and 90 meter resolution. Similarly, they are providing level 1B data that is already converted to the radians, converted into the radian. So in raw data, what you got pixel values are in the form of a digital numbers, right? So these are the number basically assigned on the basis of your radiometric resolution, right? For example, if resolution is 8-bit, then the mathematical annotation or the number system given to a per pixel is ranges from 0 to 255, right? But if you use the Landsat 1B data, that the digital number value has been mathematically converted into the radians value, right? Because when we go to the processing or pre-processing our data, we need to convert our numerical values, these digital number value, to the radians values. So if you want to download the 1B data, you can download it. That data is already radians converted to the radians. You don't need to convert into radians. That is already converted, right? Similarly, if you use the level 2 data, that has been already provided or converted into the spectral reflectance and so on. For example, if you use the *8, that is kinetic temperature, so that means digital number values has been already converted into the temperature values. So these are basically the level data, basically the process data. These are not the raw data, right? So whether if you want to download, they will provide you the link. You can download the raw data also, but you have to convert these raw data to your radiance value or reflectance value or temperature values depending upon purposes. Or if you want to download already processed data, you can already download it. There is absolutely no problem. So both Landsat data and I think ESTA data has been provided with the different levels. Okay. Enough. Okay, I think it's already, we have passes 4 o'clock. We have 15-20 minutes for further discussion, because during this COVID period, this lockdown has been again implemented after 5 o'clock. So we need to conclude this, and we again will start from this particular slide tomorrow. But if you have any question, we have 15-20 minutes. If you have any question, you are welcome to ask.
So why do we have a big pixel size in case of thermal remote sensing? Is there a reason for that?
Yeah, that I have already told it to you. For example, in 8-bit sides, if you want to use or spectral response has been recorded in the higher wavelength region, for example in thermal infrared region, you want to record this spectral response in high wavelength region, then if you want to quantize this energy, then the pixel size has been already increases, right? That is why all this data, for example your 16-bit data or 12-bit data, that is only available in the thermal infrared region. The purpose is, the advantages is your minor differences in the temperature you can able to recognize. For example, if there is any minor differences in the temperature, one pixel temperature is 23 degrees Celsius, another adjacent pixel has a temperature of 23.1 degrees Celsius, that ESTA data, 12-bit data or 16-bit data can able to recognize it, right? But if you use the higher bit data, then you have to compromise it with the spatial resolution, because it require high amount of energy to quantize the spectral response recorded in thermal infrared region. That is why you the size of the pixel is much larger. आपको एनर्जी की जरूरत ज्यादा पड़ती है उसको रिकॉर्ड करने के लिए.
Okay, sir, got it. Yeah. Thank you.
Any other question?
So for which purpose microwave remote sensing is used?
For which?
For which purpose microwave remote sensing is used?
Okay. Microwave remote sensing, we have already discussed that microwave remote sensing is recorded in the different region. That wavelength region is approximately ranges from 1 millimeter to 1 meter, right? So microwave remote sensing, if you see, is based on the radar phenomena. We will discuss that in next session. Is based on the radar phenomena. So what we do in radar, that a beam has been illuminated, it hit the particular object, and backscatter radiation has been detected. So time variance has been detected is a crucial phenomena in the radar system, right? So this is important when you want to see any natural phenomena which is related to the movement. For example, your glacier are moving. If you want to see or you want to measure the rate of the movement, then you have to go with the microwave data. If you want to see the movement of landslide, you have to go with the microwave data. If you want to see the mine land subsidence or land subsidence due to groundwater, you have to go with the microwave data, right? So this is where these are the points, or these are the areas where this microwave data is quite much important. But you cannot use this for the tectonic movement, because your tectonic movements are quite slow. It is less than 12 centimeter or 6 centimeter in a year. So that movement is quite very slow. You cannot detect these tectonic movement with the help of microwave data. For there, the other things are used. Now these days, people are using digital GPS or sensors they have used. They install the sensor in certain places at control points, and they use to measure the movement of the ground in every year. So for that purpose, they use a different thing. But for as far as remote sensing concern, you can use the microwave data to detect any type of movement, whether any movement is related with the earthquake, any movement related to the glacier movement, anything which is related with the landslide, anything which is related with the subsidence, or anything. If you want to use, you have to rely over the microwave data. That is a thing. But only thing is that movement should be very sudden and rapid. That is a thing. The microwave remote sensing, it's very difficult to measure the small response, smaller movement, smaller rate of movement, right? If the movement is sudden and very rapid, then you can be able to recognize this movement with the microwave data. Sentinel-2, radar set, NV set, all these are the microwave data sets. Okay?
Yes, sir.
Okay. Any other questions?
Hello, sir. Hello.
हाँ बताइए.
As you know, the thermal remote sensing has larger pixels. So, in whose field we can use thermal remote sensing?
We can use thermal remote sensing for measuring thermal related phenomena, right? Thermal phenomena. Thermal phenomena could be related to the coal fire. These could be related to the volcanic explosion or volcano related thing. Hot spring. For geothermal phenomena, you can use this thermal remote sensing. Okay.
Yes, sir. Thank you.
Okay. Karishma Bhaskaran has asked, could you explain the spectral resolution once again? Just hold on a second. Spectral resolution is nothing but it is a number of wavelength region is basically in how many wavelength region the data has been taken, the images has been taken. For example, in case of the Landsat ETM plus, the photograph or image has been taken in 7 respective wavelength region, right? So number of wavelength region used by a particular sensor to record a photograph or record the data, that is called as a spectral resolution. Spectral, that means wavelength range. Whenever the term spectra come, then it is related with the wavelength range, right? So wavelength range, number of wavelength range in a particular satellite data gives you the information about the spectral resolution. Higher the number of wavelength region, higher the spectral resolution. Okay. Yes, who was asking? Hello. Somebody was asking.
So I was repeating the same question from YouTube. That's why. That's it.
Okay. Okay.
So I think there are no more doubts. We can end it today.
So we will meet tomorrow and we will start from where we left today. Okay.
Yes, sir. Yes, sir.
Okay. In case you have any question, write it down. We'll answer your queries tomorrow. There is no problem.
Okay, sir. Okay, sir.
Okay.
Thank you, sir. Have a
Thank
great
you,
day.
sir. Thank you. Thank you.
Thank you very much, sir.
Thank you, sir.